our previous editions. In terms of the numbers, we are still pretty small, but we are growing. So we're not a baby conference anymore. We've had about 60 in-person participants in 2023 that have grown to about 80. We expect a little bit more today. And then for online participation, it's obviously greater. I think at the moment we have about 250 registered attendees. Now, how many attendees we'll actually have, this will show. But we are growing in numbers and people are more interested to join us, which we are very happy about. In terms of the agenda for the morning and the afternoon session, we'll have Neil starting off with UCD and computer science presentation. Then I'll have Madhusanka to introduce our NetsLab team that is also growing and have grown quite significantly since 2023 or 22 when we've started it. And then I'll have Gunesh to introduce the Robust 6G project, which is partially why we are here, as we do have our face-to-face tomorrow and the day after. So you will hear a lot about this project and solutions that we provide as part of this project. And then we have our industry and academia partners such as Thales, Telefonica, just before the coffee break. We'll have coffee in the area you were just registering at out there. I think there's some muffins and sweets there, so please enjoy your break, as this is going to be quite a long day. We'll then have Nextworks, Eurocom, Ericsson, University of Murcia with their presentations right after the coffee break. That will then end with panel discussion. So I do recommend staying for that, as we'll have 4 experts. And I think it's going to be a great panel driven by Pasika. After this, we'll have networking launch and posters. We have, I think, at least 20 posters that are prepared by our PhDs and postdocs. And this will also happen in the coffee area out there. You couldn't miss the preparation for the poster session there. So that will last for about an hour. You can go and engage with our students, exchange some contact details maybe, and look for potential collaboration with your students, perhaps. When we come back from lunch, that's from last year here. When we come back from lunch, we'll have 3 more presentations and a panel. We have University of Padua, ENSA, and Chalmers giving their presentations. And then we'll have another panel discussion. So we have 3 or 4 experts in security and privacy that will be covering a number of topics. This will end with the coffee break at 3:45. So I, again, would like to welcome everyone. We do have more people coming in as well. And we'll start off with Neil and his presentation about our college and our school. Let me.
Good morning, everybody. So I'm Associate Professor Neil Hurley. I'm the Head of School of Computer Science here in UCD. Here's a picture of the front door of our school. And I guess my main purpose here is to welcome you all to SECURENET 2025. And I'll say just a few words about our school in general as well as part of that welcome. It doesn't seem like that long ago that I was in a similar room across campus opening the first SECURENET Summit on security and privacy in future mobile networks. And I can see that, as Bart showed you there just a few minutes ago, that the conference is growing from strength to strength, increasing its numbers and its activities over these few years. And I expect that to continue over the following years. The nice thing about this event is that it's an event that brings academics and industry together to discuss next generation networks, security, robustness, and all the things that are driving technology and research in this area into the future. I can see that this year Summit is going to have an exciting program. I see a strong theme of AI throughout many of the talks today, addressing sort of the network issues that are driving this area: 6G networks, automation, trust management, authentication, and so on. There'll be an interesting lunchtime poster session, which will showcase some of the research that's going on. 2 panel sessions, which I hope will generate lots of questions and discussions. What I want to mainly do here is thank the sponsors of this event, which are Madasanka's Net Lab, the Research Ireland Connect Centre for Future Networks, and Robust 6G project. But let me say a couple of words about our School of Computer Science. We are a growing school. After our round of recruitment that will take place, that has been taking place over the last couple of months, I expect that our faculty will grow to over 70 faculty members this year, including our operations and research staff. We've got over 200 staff in total in the school. And thinking about the number of students in our thought and graduate programs, we've got about 1,700 students in total. And these are students who are in computer science programs. We're not a service school that serve modules out to other schools. These are programs that are run and managed and developed by the School of Computer Science. In terms of our research income, we average around about 10 million per annum over the last 5 years. We have a very active research staff, and we like to think of ourselves as a school that trains the next generation of computer scientists on cutting-edge technology delivered by research active staff. The research areas that we are working in, well, AI is all over the place. It has managed to jump outside computer science and is going across all of the discipline areas in the world at this stage. But we've been working in AI and data science for, I guess, 20 years or more. We have the Insight Centre for Data Analytics, which is a Research Ireland sponsored research centre here across many institutions in Ireland. But a large amount of the activity that takes place in UCD in that research centre is through academics in the School of Computer Science. We also have the CEDAR Enterprise Ireland Technology Centre for Applied AI, which has another 50 researchers working with industry, helping them to upskill to bring AI into their business. Both of these centres are also growing, and well, hopefully growing, because they have both applied for phase 3 funding within this year. So our hope and expectation is that we will see another 6 to 8 years of development of these areas. And we have around 20 or 25 academic staff who are working directly in these research and technology centres. But AI is one major pillar of the research work that we're doing, and it's important to diversify across other research areas as well. When I look across the School of Computer Science, the major themes that emerge in our school is one of cybersecurity and forensics. So we have, again, a more than 20-year activity around forensics, where we have developed a thought program which is targeted towards law enforcement and has been a very successful program in training our own Gardaí, our own law enforcement here in Dublin, but also across Europe and into Asia and the United States as well. We have a big area in secure software engineering, and the area that we're talking about today, future networks. And another emerging area which is growing in strength is the area of human-centered computing. So if we think about the research that's going on across the school, these are the major areas. I've mentioned there are some of the research centres that are supporting this research. Lero in the context of software engineering, Connect in the context of the future networks. And we'll be looking for ways to develop and extend that funding into the future. So what is the future for the School of Computer Science? We are continuing to expand, targeting the recruitment of research ambitious academic staff. We're helping to develop UCD's breaking boundary strategy. So this year, UCD released its strategy to 2030. So the strategy for the next 5 years. And a number of themes come out in that strategy, which are very much related towards the work that we do in the School of Computer Science, in particular AI and sustainability. So we look to be leaders in driving the delivery of UCD's strategy in these areas. Of course, AI has brought lots of opportunities to computer science and lots of risks as well, insofar as it's disruptive across a lot of industry, but in particular across the computer science, the technology industry. It's disruptive in the industry itself, and also disruptive in the way that we train and teach people the skills required for the industry. We're doing a lot of work on developing our curriculum and our assessment strategies in the context of AI and LLMs, and we need to move rapidly in order to keep up with a rapidly changing sector. We're also rapidly developing our curriculum by developing new programs that cater for the sector. A couple of years ago, we brought in a new program in cybersecurity aimed towards professionals in the industry, which can be taken while you're working in industry. It's delivered largely remotely to make it available to people who are working. This year, we're bringing in a new master's targeted at advanced AI. So realizing that a lot of bachelor level students or people working in industry have developed the basic skills in AI, we saw a gap in the market to actually help people go to the next level of developing advanced skills in AI. And that would be started and delivered from autumn of this year. And we're also trying to deliver training to industry. We're trying to expand our micro-credential courses. We already deliver a lot of cybersecurity courses in micro-credentials rather than in full programs. And we're extending that into forensics and into machine learning and artificial intelligence into the future. So that's all I want to say here, except for to say welcome again to SECURENET 2025. I hope you have a great day. I hope you have lots of interesting and fruitful discussions. Make the network connections that will help you to develop your own career into the future. That's what this is all about. So I hope we see lots of interaction and engagement during the day. So thank you very much and have a great day.
So good morning, everyone, and I would like to welcome you all for the SECURENET 2025 event. So I think this is the only Ireland's flagship 6G security forum, which is happening for the last few years. So we are at the third summit. So I'm glad to see this is going for several years continuously. So I'm Madhusankar Liyanage. I'm an associate professor at University College Dublin, Ireland, and also I'm the director of NetLab research team. So the SECURENET event, actually, the idea of the SECURENET event came for a couple of years back. So where we saw there's a lacking of a forum in Ireland to discuss the 6G security. So we started to think about developing a platform so where we can discuss the security and privacy challenges of 6G network, and also above all, like to discuss like what are the new solutions which we are developing in the different projects, especially in the European project. So we always invite one of the project partners to support us in this event. And this year, we got a lot of support from the Robust 6G, and we got all the speakers from the Robust 6G. And I would thanks for the Robust 6G team for participating in this event. And also, we have this Connect Research Ireland Center for Future Network, and they are also supporting to organize this event. So I would like to say, like, as per yesterday, like we have like 291 registration from 23 countries. So I think it's a quite global event. So a lot of participants are participating from the YouTube and also from the Zoom link. So I think it's a very much popular, becoming very much popular, and I think we can do like a global impact with this SECURENET event. And I want to introduce about the NetLab, so the main sponsor for this event. So the NetLab is the Network Softwarization and Security Laboratory, so which is a research group in UCD School of Computer Science. So primarily focusing on the security and privacy of the future mobile network. So at the moment, we are focusing on the 5G and 6G network security and privacy. So I'm the director of this lab, and we have more than 30 members, including two co-directors, Dr. Pasika and Dr. Shen Wang. And beyond that, we have 4 postdocs and more than 20 PhD students and several other visiting PhD students and the research engineers. So when we talk about the research agenda of the NETS lab, so we are working under 3 different pillars. So one pillar is the AI security and privacy. And the second pillar is like how we can implement the blockchain in the 5G and 6G network. And the third one, we are focusing on the network softwarization and the security automation. So under the AI security and privacy, we mainly focusing on the federated learning scenarios, like how we can use the federated learning to improve the 6G security, especially for the anomaly detection or intruder detection systems, how we can adapt the federated learning system in these scenarios. Beyond that, we are also working on like how we can ensure the security of the federated learning system, both security and privacy, what kind of techniques we can use to improve the federated learning system. And also we are started to working on the explainable AI, like how we can adapt the explainable AI in order to develop like a resilience and more explainable AI security models, and also how we can use explainable AI metrics in order to improve the AI security mechanism. And since the last few months, we are trying to adapt this AI security solution in the ORAN systems as well. In the second pillar, it's about the implementing the blockchain in 5G and 6G network. Initially, we started working on using blockchain in IoT application and also IoT data management mainly. Later, we started to move towards the more mobile related application like spectrum management scenarios. And also we started using NFT or non-fungible token based resource sharing on the spectrum management and also for the network slicing resource management area. So since recently we started looking at like how we can use blockchain for trustworthy AI data management aspect as well. In the third pillar, we are looking at the network softwarization and the security automation domain. So mainly this is related to the 5G related research areas. Like we are looking at the network slicing, multi-access edge computing kind of technologies and see what are the security challenges and how we can eliminate these challenges. Especially we try to develop new security protocols to ensure the security of these network slicing and make scenarios. And recently, we are focusing more on the security orchestration side, how we can enable the zero trust security management, so we can have like a automated security deployment in the 5G and 6G network. And NetLab is mainly involved in quite many projects. So I think our main funding partner is the 6G SNS. So we are full members of 2 6G SNS projects, Confidential 6G and the Robust 6G project. And recently we are focusing on the deployment of our security solution in the different infrastructure projects. So we are part of FIDAL 5G, 6G Sandbox, and the 6G Brick, where we are implementing our solution on top of the real 6G network scenarios. And also we are part of several other EU projects like Spatial and Ensure 6G. Ensure 6G is a Marie Curie staff exchange project. And also we are contributing to the local funding projects like the Connect and ML Lab in Ireland, and also 6G flagship and the 6G Cure in Finland. So a little bit about our project. So Confidential 6G is the 6G SNS project, and it's mainly focusing on 3 pillars of 6G security. One is develop the post-quantum security and the privacy preserving cryptographic mechanism, and developing the confidential computing security mechanism and the confidential communication mechanism. So in UCD, contribution is mainly working on like how we can use this post-quantum security mechanism in the 6G network, and also develop the secure federated learning system, and also blockchain-based solution, like especially for the dynamic spectrum management, how we can use the blockchain-based solution. And the robust 6G is another 6G project. So I think Gunesh will give more detail about the robust 6G project, what we are going to do there. And it's mainly focusing on the automated and smart security. From UCD side, we are mainly focusing on the federated learning, especially the peer-to-peer federated learning, how we can mitigate the security and privacy challenges in this peer-to-peer federated learning system, especially using the explainable AI technique. And as I mentioned, like since the last year, we focus more on like the implementation related research work. So we have our own 5G test network, ORAN 5G test network, which is available in the computer science. So using this 5G test network, we try to build different use case applications. So one of the application we did under the FIDAL 5G is to implement this VR medical application over the ORAN testbed. So with one of the SME in Greece, so we use the VR headset and the gloves which they have developed, so we can have like sub millisecond communication between the gloves and the VR headset using the 5G. And we have demonstrated using our own testbed, and also we did it in the Petra's testbed under the FIDAL 5G, and also the cross network implementation as well, to see how this application running on top of the 5G. And now we are part of this 6G sandbox project under the ARMOR project. So what we are doing is like we are trying to deploy AI-based XApp on the ORAN test network. And also we are developing a platform where we can test the security of this XApp which we are deploying in the ORAN test network. So we using the explainable AI to understand why these security attacks is happening in the AI system, and we try to use the LLM to generate some human understandable explanation. What is the reason for these attacks? So we try to automate the whole process. So before you are deploying any XApp, which can be tested, and you can get a report like how vulnerable is your XApp in the ORAN setting. And we recently got funding for this collaboration XAI or Collab XR project. So this is actually extension of the FIDAL 5G project. So in the FIDAL 5G, we did only the single user experiment. So we are trying to do is a multi-user XR application over the 6G network. So where we can have like a sub-millisecond communication can be enabled with this ORAN testbed. And also, as I mentioned, like we have our own 5G test network, which is supporting full scale ORAN deployment with the 7.2 split. We have 2 base stations. And also from the core network side, we are not only supporting the ORAN, we also supporting the blockchain implementation, and also the network slicing, edge computing implementation if you want to do any kind of 5G deployment. And also we are supporting the AI application. So we are supporting the federated learning platform on top of our network. And we have several IoT devices to support this real-time federated learning deployment. And apart from that, we have several VR headsets, so we can support the VR and AR application as well. And also, we are working on the development of the different type of data sets. So as a service for the community, because we know like there's a shortage of data set in the 5G and 6G domain. So we have already created 2 data sets. So I will start with this 5G and IDD data set. So actually it is done in the 5G test network in Oulu, where we have a comprehensive intrusion detection data set. And also we recently published this NestLab 5G ORAN dataset. So we have collected the data in the 2 different levels, where we have the application layer data and also the radio access level data. I think this is the very first time we have published any radio level information as a dataset. So both of these datasets are publicly available. If you go to our website, you can download it. So, and we focus on more and more dataset creation, so it will help for the community. So thank you very much. So that's all about the Nest Lab. So we invite you to follow our website. And if you have any questions about the project, so we can discuss during the coffee breaks and also the lunch break. Thank you.
So we're now moving on to the technical section with the first presenter, Ganesh Kashik, presenting the insights of the robust 6G project. Just find that presentation very quickly. Oh, it's being transferred on the go. We'll have a very high-tech system for time tracking. So there will be what do we have? 10 minutes?
How can I like?
Just press the right arrow
Okay.
or
Okay. Okay. Hello, everyone. First of all, I would like to thank UCD team for such a great organization and hosting us in University College Dublin. For the ones who don't know me, let me introduce quickly myself. I am Güneş Kesik, and I have been working for Ericsson Research in Turkey since 2021. And my current role is Research and Innovation Engagements Manager, and I'm taking care of external research collaborations of my team with universities and other research institutes or companies across Europe. And recently, I have taken care of the coordination of Robust 6G project on behalf of the consortium since last January. And in this presentation, I will briefly talk about our project Robust 6G. I will give some administrative details about our project and the consortium and the motivation and context behind Robust 6G project, the objectives and approach that we have implemented so far, and architecture, our current or latest architecture, and the use cases that we are going to demonstrate our technical or technological innovations through. Robust 6G project is the abbreviation of Smart, Automated, and Reliable Security Service Platform for 6G. This is the title of our project, and Ericsson Turkey has taken the global project coordinator role for this project. And we have a technical management committee, which is led by University College Dublin, BART, and supported by University of Murcia and University of Padua. And the duration of our project is 30 months, and we already in the middle of the project, and we are hoping to deliver some some prototypes around September. The overall budget of our project is for the 2 million, and our project has been funded in the second phase of SNSJU program together with 4 other projects in the same stream or same call. Right now we have 14 partners in our project, and we have 7 universities, 3 large enterprise companies, including Ericsson, Thales, and Telefonica, 3 SMEs, Nextworks, Axon Logic, and GOM Electronics, and 1 research institute, Eurocom. And in general, we have partners from 7 different European countries. I would like to briefly mention about the motivation why we initiated such a project. First of all, as you know, it is anticipated by the 6G ecosystem or the telecommunication ecosystem. When the convergence of digital and physical worlds becomes a reality, the 6G networks will be asked for more. Asked to fulfill far more, challenging requirements and serve for more demanding use cases such as massive digital twinning, holographic telepresence, and immersive communication. Of course, to manage this complexity, we need to implement a paradigm shift here towards full automation of the networks. These, networks, because these networks have to be programmable and adaptable to the different needs or the diverse needs of anticipated 6G use cases. But of course, this comes with certain challenges, by enabling such programmability or flexibility, we will foresee an expanded threat landscape for 6G networks. And there will be potential or maybe some cyber risks, cyber security risks, and as 6G networks or we have to tackle these security challenges to ensure the trustworthiness of 6G networks and enable its acceptance by the society or by the ecosystem. So, of course, in order to manage, this complexity or we have to enable the usage of AI ML across the network, and we are expected to see that AI ML will be heavily used, within the networks to automate decision making, to enhance performance and achieve zero-touch automation and end-to-end trustworthiness for 6G networks. Of course, these AI ML have to rely on, or AI ML solutions have to rely on data, and we have to ensure the security and privacy for data management. And this is, of course, a significant challenge. And right now, we are trying to address, these challenges within Robust 6G project. And in order to provide the acceptance of these systems by the society, we have to ensure that they are trustworthy, they are robust. So these trustworthiness of AI solutions, that's why it's paramount importance. We have to, of course, there are certain regulations such as GDPR, such as EU Act, the EU AI Act. We have to comply with these regulations and make sure that our solutions comply with these requirements. But on the other hand, when we try to implement such AI-based solutions, we have to rely on maybe efficiency, but of course, we have to ensure that these solutions are energy efficient. That's why there's a trend in the ecosystem that green and sustainable AI methodologies are promoted. And by considering all these motivation elements and the context that we are in, we have designed Robust 6G project in order to provide data-driven AI ML-based security solutions through zero-touch network and service management framework to or for fully automated end-to-end smart network and service management for 6G. To do so, to all these, we are relying on secure and privacy-preserving distributed intelligence, privacy-enhancing solutions. We are using explainable and sustainable AI methodologies We are focusing on trustworthiness at the physical layer and use of physical layer information to provide end-to-end intelligence for 6G networks. So this is shows the high-level architecture and the VP distribution or work package distribution of our project. As I have already highlighted, we have right now we have four different technical work packages, or four main technical work packages. In work package 2, we are mainly focusing on the overall architecture and one of the key important elements of our architecture, which is data management platform. In work package 3, we are working on trustworthy and sustainable AI services, and we position this work package and the outputs of this work package as a source of these trustworthy and sustainable AI services, which will be used across the network. And in the fourth work package, we are focusing on the use of these AI solutions through zero-touch security management frameworks. And we have been working on programmable monitoring platform, which is again an important element, and which tackles the collections of different data sources related to the security or the overall status of network from different devices, different network elements. So in work package 5, we are working on physical layer security related innovations and technologies. And in work package 6 of our project, we are focusing on mainly the integration of all these solutions and showcase our innovations through the use cases that I will briefly mention later on. And this shows the final or the current robust 6G functional architecture. In this functional architecture, or we foresee that all these functionalities will be run on the common cloud platform. And on the right hand side, you see this programmable pervasive monitoring platform, which has which is responsible from collecting data from different network elements. The data this module collects could be fault information, or potential attacks, or maybe the status of different devices within the network. And this programmable pervasive monitoring platform is quite flexible and designed to be dynamic enough to address all monitoring requirements of 6G networks. And this it is also responsible fetching all data and feeding data management platform. This data management platform is responsible from the overall management of data used within the networks, and it has internal data security, data catalog, and data fabric functionalities, and it secures or manages the secure access to data for external and internal users. And we have physical layer security module, or physical layer security functionalities, which is running in the run layer. And these physical layer security solutions are trying to address or trying to detect potential attacks and mitigate at physical layer. It has also have local closed-loop mechanisms to act on potential attacks promptly without creating further delay by communicating with the upper layers. With zero-touch security management layer, we have this zero-touch security management layer provides the overall security orchestration and management for robust 6G project. It has closed loop functionalities. It has resource orchestration and security orchestration functionalities, which orchestrate or manages, security operations and the resources used within the security operations. And lastly, like we have trustworthy and sustainable AI services layer. As we have already mentioned, there will be like, different AI functionalities, including explainable AI services, sustainable AI services, distributed federated learning framework, and so on. And this layer will also be responsible from the management of the life cycle of, AI solutions, and it will be working as a source for different AI functionalities, which will be used across the network. So that's why we will have many interactions between different layers with this trustworthy and sustainable AI services layer. And lastly, like, we will expose all these, functionalities, all these security functionalities towards the external ecosystem through our exposure framework. And in order to, like, showcase the solutions that I have briefly explained, we will have 3 use cases. The first use case, we position it to assess the trustworthiness of the proposed AI solutions. So in the first scenario, we will be focusing on decentralized federated learning for joint privacy preserving machine learning and deep learning model training. In the second one, we will be showcasing physical and sensing layer trustworthiness and ensure the resilience of the 6G networks end to end. In the second one, this use case will be, showcasing. Okay, sorry, my time's up, but I will, wrap up in 1 minute. For automatic threat detection and mitigation in 6G-enabled IoT environments, of course, there will be strong interactions with the trustworthy and sustainable AI services layer, and zero-touch security management and orchestration layer, and data management platform. This use case is positioned to showcase all the innovations that we have in the robust 6G project end to end. And lastly, in the third use case, we will expose all these functionalities through robust 6G exposure framework and integrate our solutions with the camera gateway. And I guess, I have finished my presentation, but I shared the QR code of our project. As I said at the beginning of my presentation, we will be delivering our first prototypes in month 21. Please, follow our, website and social media accounts. And if you have any, questions, you can reach out to me or any partners that we have in Robust 6G Consortium. And thank you.
Any questions? Please let me know, or catch Ganesh during the coffee break, maybe. And now we're moving on to the next technical presentation by Thales. See, we have it here. Right. Control. Oh, you will have to use the arrows or the Greg, and 10 minutes, 5 minutes, and 1 minute. Okay.
Okay, so thank you. Good morning. I'm Duha Ayed. I'm a security expert working now in the new Cortex labs of Thales that are mainly dedicated to AI research activities. And I'm mainly in our cybersecurity lab, in Cortex Labs, in charge of the roadmap related to security of 6G. And today I'm going to talk about the AI nativeness of 6G and its impact on security. The last part of my presentation will include a small talk about the vulnerabilities of AI, which is a work related to my colleague, Katarzyna Kapusta. So let me first address the lack of a clear definition of the term AI native. And for that, let's observe how this term is generally used. So AI native is often used as a prefix to an entity that could be, for example, a function, an implementation, an architecture, and so on. And regardless of which entity this prefix is used for, the concept is always the same. It means that there is a usage, a pervasive usage of AI with the required accompanying data infrastructure in all the components of the entity, rather than adding an AI-based component to an existing non-AI-based entity. So this means that ideally, the AI should be designed as a first thought in the system and not as an afterthought in the system. So what does this mean for 6G systems, or what does it mean for a system in general? This means that the system or a 6G system has to be designed in order to leverage AI and to achieve a zero-touch network management. So an evolution toward zero-touch network, a full end-to-end network, and the real service automation is becoming a necessity in order to manage the complexity of 6G. So the ultimate goal is to have a highest degree of automation of the management and each functionality, while enabling a full autonomous operation of the network of its security. So this automation should be driven by the high-level business goals and policies, and the network should be able to self-manage and self-organize. So in order to realize this vision, we definitely have a need of a novel architecture and a novel enabler that support near real-time closed loop and that is designed to integrate AI functionality and that is also optimized for data-driven analytics. So for that, the ETSI did a great job in specifying the ETSI ZSM, which is an architecture and a framework about zero-touch network management. What is really good and interesting in this framework, it's that beyond the fact that it's designed in order to integrate and to have capabilities that are AI-based, it is built on a service-based architecture which adds flexibility, modularity, extendability, and so on. And it also supports separation of concerns of various what we call management areas, where you can see here a real separation between, for example, data collection management, analytics, and also the intelligence management domain and the orchestration and control domains. So for this reason, and for many years now, Thales, for example, is focusing on the instantiation of this framework for security. So, because till now everything is good, AI nativeness, enablement of closed loop, and so on. But what is the impact of security of this AI nativeness on security? So let me start with positive things. The positive things is that security solutions should follow the same pattern of AI nativeness, of AI enablement, and so on. So, as I said before, for this reason, we had in Thales, for example, we have had a special focus on the association of this infrastructure for security solution. We started this work, research work at the European level, mainly with the partners of Inspire 5G+, and we are continuing now in the context of robust 6G. And our first focus was mainly on having an automation of the security orchestration and security management based on security policies and service level agreement that are focused on security. So as you see, this infrastructure and framework had a dedicated also management area for security, going from data collection of security, analytics, decision making also based on AI, and so on. And as I said, the first focus was the automation of security orchestration. And now we are mainly focusing on having a real closed loop based on AI for security. So for sure, what could be interesting is using various types of AI for decision making for security, because there is enough of complexity. For example, we see the decision on where to place security function, how to place efficiently a security function. But the added value of AI would be for sure to have a good balance between, for example, security SLAs and other types of SLAs. Because the problem of security is that it is expensive. It's expensive in terms of several meaning. It is expensive because in general, it's difficult to sell security just for security. And then it's also expensive in terms of performance, in terms of, yeah. So AI could help to find a good balance between security service level agreements, for example, and other types of service level agreements. And also to find a good balance with the business goals also. So this is important because without AI, it's a very difficult problem. So then, so here I show some examples. For example, in Thales, we are working on in order to have the usage of AI in decision making in such closed loop. For example, using neural network training to train a function in order to decide where to place a security function when we have as input a network with a set of nodes and a connection, on which connection should we place the security functions, and on which nodes, and what are the security functions that we have to place. Also, the usage of reinforcement learning agent to take decisions on actions, for example, that have an impact on the status of the system. For example, adding a node or deactivating a node after an attack. And these actions are taken based on a reward that represents an optimization function in order to optimize the security service level agreement and also other service level agreements related typically to performance. Then I have other examples of the usage of AI, for example, in security orchestration and response process, in order to have a sort of autonomy for responses, like it could be, for example, the usage of generative AI in order to generate security rules for detection of new attacks. We are now experimenting the usage of generative AI in order to generate the workflows related to the response to attacks. So then, there is a but, and this is the second type of impact that is probably less positive, is that AI has a lot of benefits when it is used in solutions for security, but it has many vulnerabilities. Here you have a panorama of several types of attacks that could happen for AI in several that are presented in several categories. The first category in blue, it's type of attack that will target the efficiency of your AI model that we could change by evasion the behavior of the AI model. For example, if your targeted objective is to recognize some image, if there is possibility to poison the data that is given as input in order that the recognition processes differently and cannot recognize what you want to recognize. Another type, you have other types of attacks on the other side of the slide. For example, the attacks that can target the privacy of the data that is used by your model, or directly target the model itself. There is possibility of model theft. And then there are a set of attacks that are specific to generative AI, such as the prompt injection and the RAG poisoning. Regarding the solutions, I will give a set of solutions, but I think that there is a presentation that is dedicated to the cybersecurity of AI, where we can also discuss some details related to that. So there is definitely solution in order to protect the model itself, like the model encryption using homomorphic encryption, or using a multi-party computation, or obfuscating the model. And there is also a possibility to use confidential computing in order to protect all the code and also the data of the model. So this, of course, limits the knowledge about the model and makes the privacy or the evasion attacks very difficult. But be careful, because models prediction can reveal more than we think. The attacker can still deduce about training that data, like member inference, model inversion, and so on. There is also possibility to extract the model through its API. Then, again, about the model protection and also the sensitive data protection, there is a possibility to have a collaborative training and let the sensitive data locally in order to not centralize it. And then another way in order to have a protection of the model and adding a sort of traceability for the model is watermarking the model. Watermarking is a secret modification of the model, and once it is revealed, it shows, for example, that the model is belonging to an entity. For example, in Thales, we worked on a solution that shows the logo of Thales. Okay, so to conclude, the evolution towards zero touch and full end-to-end network and service operation is becoming a necessity in order to manage the complexity of 6G, and security solutions have to follow the same pattern of AI nativeness of 6G, where the AI should be implemented as first thought in our system and not as an afterthought. So there is a coverage of 2 dimensions in the presentation, the AI usage for security solutions, and then the cybersecurity related to AI. So AI can be valuable, but it is not, as you understood, not free of vulnerability. But the good news is that the security of AI can also leverage classical cybersecurity countermeasures. Well, thanks for your attention.
Hi, I'm interested in your use of watermarking to mark AI models. Are you using similar techniques to the watermarking of media content? You look at fragile watermarks or robust watermarks?
Actually, in our lab, we are now a lab of AI. So our research work is mainly focused on how to watermark AI model in order to have traceability on the model, even if it's used for someone else, it belongs to, there is a possibility to always see that it's model of Thales.
But when we watermark, we usually find some signal. It could be an audio signal or an image signal after watermark.
Yeah.
What sort of machine learning model signal would you use watermark? Where do you put the watermark, I guess?
In the models of AI models? I do not really know, because this is, as I said, the work of my my colleague Katerina, but I can ask the question and share the response.
So now we move on to Telefonica. We have Lucia Canabias Rodriguez. You're the only presenter today, right? Right. Yes, so it's either the arrow or you can click on the mouse, whichever you think is easier for you.
Okay.
Okay.
Thank you.
Hello, everyone. Thank you for attending this session. I am Lucia Cabanillas. And I'm presenting a joint work between Telefónica and UC3M. This is a collaborative effort with Juan Manuel Montes and Pablo Serrano from UC3M and Diego Lopez from TID on enhancing access control to network services by identity assessment. So let's start. But first of all, let me explain what was the motivation for this work. Traditional access control mechanisms like airbag and ABAC rely on static policies. Airbag assign permissions based on roles, and ABAC assign permission based on contextual attributes such as the username. While useful in stable environments, these models can adapt to fast-changing security threats or scenarios. For instance, these models don't account user behavior, which is key to detecting insider threats or identity misuse. This motivates the need for a behavior-aware adaptive access control mechanism. So what we have been working on is to improve access control mechanisms by analyzing how a user or a device behaves in real time. We use explainable machine learning models to generate a trust score, which reflects how trustworthy or expected the behavior is. And our model does not block or allow the access. It explains why, which will allow us to understand its decision. But let me explain the architecture of our work or our approach. We have a user who wants to access to a protected resource. This could be any application or service. And this is governed by an access control mechanism that could be in the data plane or in the control plane. But let's look at the guts of this access control. We have the policy administration point. This is responsible for managing the policies. These policies define who can access what and under what conditions. Then we have the PDP, the policy decision point. This is the core of the decision-making process, since it will be responsible for evaluating the policies and making decisions based on them. And the key distinction is that the PDP will take into account static rules such as the role, the username, but also will take into account the user behavior. As the user wants to access the protected resource, the user should initiate an authentication request to the IDP, the identity provider, which will be in charge of verifying the user credentials and issuing tokens. But one key distinction is, as we want all actions in our system to be secure and allow, the identity provider will send this request to the policy enforcement point, and the PEP will forward it to the PDP. The PEP acts here as a gatekeeper, enforcing the decisions made by the PDP, and the PDP will analyze things such as the authentication protocols being used. So if all conditions are satisfied, finally, the identity provider will issue an access token. And now the user can use it to send a resource request to the policy enforcement point. But the thing is that in our model or in our system, the accounting layer will be capturing and storing all the interactions with the network. This is crucial because the accounting layer will contact to the explainability module, which use this data to analyze patterns, anomalies, or deviation. And the explainability module will send to the PDP a trust score, which reflects how trustworthy or expected the behavior is and explains why. So the PDP will make in that sense, a more informed decisions. And if all conditions are satisfied, the user identity, the authentication protocols, the user behavior is trustworthy, the roles, and so on, finally, access to the resource will be granted. But let's delve into the explainability module. Let me explain it in more detail. As I already introduced before, the accounting layer so important because it's monitoring the complete behavior of the user. And this is crucial for the explainability module since it needs some sort of memory to store the patterns of the user. In the proof of concept that I will present later, we analyze a WLAN where we monitor in the accounting layer features such as the access points, the traffic activity, the IP addresses, the port use, and the time of arrival. To evaluate the behavior of the user, we rely on a trust assessment. This is computed by analyzing the user current activity to its historical data. The system builds two profiles, one based on past activity and one in real time. And the system compares both profiles and with numerical and categorical features. This produces a trust score, which goes from 0 to 1 and reflects how closely the current activity matches the behavior profile. Also, we use explainable boosting machines. These machine learning models does not just provide a decision, it also explains why. Because if the user receives a low trust score, the model will highlight what behavior triggered the suspicion. And now let me explain in more detail the PDP. In traditional access control mechanisms, having the right role was enough to get access. Trust was binary. If you had the admin role, you were trusted by default, and access to the resource was granted as long as you had the right role. But now, even with the correct role, users must prove consistent behavior to gain access, and access will only be granted to those users who comply with all conditions and are who they say they are. So in that sense, we will be adding another layer of security because we will be checking before making a decision if the role corresponds to them. But how we define and enforce the policies. We use policy as code with Rego, which defines and manages access control logic programmatically using a declarative language, which allow us to set up or configure any kind of policy because you can check the role, the username. You also can verify the signature of the access token to check that it comes from our IDP and it has not been altered along the way. You can also analyze the body of the request and send requests to another module. So the access rules will adapt in real time based on behavioral insights from the explainability module. So in that sense, the policies will be transparent, traceable, and can be version control, and will allow us to find granularity. This will be a representation of the policy that we configure, where we extracted the access token and decode it. Then we validate the role. This information is within the bidder token. Then we send an HTTP request to the explainability module to fetch the behavior data and validate if the behavior score is high enough. And finally, we validate if the IP is trusted or familiar. Depending on whether all conditions are met or not, access will be denied or granted. This is how the policy looks like, just like regular code in Rego. And finally, I just wanted to introduce a proof of concept that we did. We tested we tested the explainable behavior on the WLAN of the UC3M. This scenario had almost 300 access points, and this scenario is especially interesting because it has many different users with different roles, private resources, and private databases and resources that can only be accessed from certain IPs. We obtain a degree of trust at each moment. We can see that in the morning it's very low, since the malignant actor is using different IPs and different access points, and the model highlights that these features affect the behavior in a negative way. However, as the day goes on, we can see that confidence on this user grows, as the right user in that case is using common access point and the same user agents. So access to the resource or the private database will be granted. We can see that the model highlights that the user is using different IPs and different ports, but also highlights that there are other features that affect in a positive way. Just to finalize, I just wanted to mention or say that we can say that we have enhanced access control to network services by identity assessment, since we will be adding another layer of security by analyzing user behavior. We leverage, or we have used explainable machine learning for real-time, transparent, and decision-making, which allow us to understand each decision taken in our system. We successfully tested it in a real-world setting, and we provide actionable insight to improve security policy for enforcement, since it's not just about deny or allow the access, it's about continuously learning and strengthening security. So looking ahead, our main goal will be to explore new use cases requiring more complex and adaptive models, combined with external threats detection systems to improve risk identification, and finally integrate both models. I just wanted to mention that this work has been partially funded by the European project Robo 60, and that's all. Thank you so much. You can repeat the final part. Maybe. Since you are storing or capturing the complete behavior of the user in the counting layer, but you are strengthening the access control to private databases or private resources.
Okay, there's at least three more. Okay, so there you go. Yeah, go ahead.
Thank you. My question is about the collection of data related to the behavior of the user in order to assess the level of the access that he has. At which level this data could be private, and at which level you are allowed really to use it, even for granting access.
In that, in the proof of concept that we did, for instance, we monitor the data captured on the WLAN of the UC3M. This data can include the most common access points, the traffic activity, or the IP that shouldn't be private. So I have the features that we capture the most visit access point, the traffic activity, the IP addresses, the port use, or the time. So I think it wouldn't be a problem. Like that.
Yeah, I think the problem is not what you input, but what you output. So whatever, no matter what we are collecting, if you are inferring the behavior, then there is a privacy problem there.
Done.
Michelle, I see you had a question there.
Yes. Hi, Lucia. Thank you for the presentation. I have a couple of questions. You mentioned that this is based on machine learning, right? So I wanted to, which kind of, I was wondering which kind of machine learning algorithm you've been using, and also how you train it. So it's totally data driven. So you basically base your training on the behavior of the user by checking the history of what this user does usually, or you also have some side information, some model about the user that is injected maybe by the system administrator on top of that. Also, I'm curious about the threshold. You say that it is rule-based and you have a sort of threshold so that if you are below or above, then you make a decision. So I wouldn't know myself how to set the threshold value. So that is quite, yeah, thank you.
Regarding the first question, we use the explainable boosting machine that's that kind of explainable machine learning model that not only will provide us a trust score, but also will explain why, as we saw here, this figure on the left. Also, we train this machine learning with the monitoring data stored in the accounting layer. So in that case, the model will build two profiles, one based on the past activity and one based on the data in real time, and then compares them and with, in that case, with categorical features such as we saw the most common access point, and numerical features such as the IPs or the ports. And based on that, generates a trust score which reflects how closely both profiles matches. And so I don't know if I have answered your question. And the third one, regarding how we can say if a user is trusted or not. What we configure is that if the trust score is high enough, in our case it was 0.8, so 80% was trusted, the user. But as we saw here, the access to the result will be granted only to those users who comply with the static roles that we saw. In that case, I have represented only the role, but the user must comply with the role, the attributes, and the other things, and should access will be granted to those users who are who they say they are. So
the threshold is experimental. Thank you.
Okay. Is there any more questions? Okay, fantastic. Well, thank you, Lucia. That's great. So we do now have a coffee break. So let's all go outside near the poster session. There's coffee and some scones there. We can wake up a bit, recharge, and then we'll come back for another set of technical presentations and then the panel. So I'll welcome everybody into the corridor where you can find coffee. Right, so, hi, everyone, again. We can resume here. I have Pietro Gardina from Nextworks, right from sunny Italy. So the stage is yours. If you have any questions, we do have time for questions at the end, so please don't be afraid to ask. Yes. Unmute. I am unmuted. Yeah. Okay.
That's okay.
Perfect.
So I can use the arrow, right?
You can
or-
use the arrows or
or the
you can
mouse.
use the mouse.
Okay. So, first of all, thanks for this. Yeah, that's okay. First of all, thanks for this opportunity. You see the colleagues. I'm Pietro Giardina from Nextworks. Nextworks is an SME, Italian SME, very active in European project in this context and also in mobile, for mobile networks. I'm covering the role of R&D deputy technological leader, whatever it means. So I will try to provide you an overview related to the security orchestration and automation in 6G, with particular focus on the work we are carrying out in robust 6G. So I don't have to tell you that the automation is one of the key aspects of the modern cybersecurity. Well, there are a lot of motivation for this. For example, it automates repetitive tasks so that security teams can focus on more interesting things related to the security, improve the efficiency and speed. This is a consequence of the first point, of course. Reducing the human error, this is important because we are not made for repetitive tasks. So sooner or later, we will make a mistake, okay? Enhance the security posture, that's for sure, because it's basically if you address the vulnerability in your company and you respond to threat promptly, of course, we enhance your security posture. And it exists a number of different tools and frameworks, okay? Platform, whatever, for orchestrating security, automate the security. And one point I didn't report it here, and this is probably the most important point for, few managers, it reduces the costs. So the operational costs of the security, okay? So how the security orchestration automation is performed now, currently? Basically, these automation techniques are based on execution of predefined playbooks, okay, that handle common security incident. This is executed by SOAR. I'm not saying anything new, okay? So security orchestration and response, which is a tool or a set of tool or platform for security orchestration and automation. But the threats can be also identified by SIAM, Security Information and Event Manager, with those fancy interface. This is more an analytics tools. And the SOC, the Security Operations Center, exploits both of them. You can exploit one or two, one or the other, or both of them to implement and automate security responses. As I said, this reduces the manual workload for the security team. To conclude this introduction, let me introduce also the NIST incident response model. So the National Institute for Standard and Technology incident response model. You can see here revision 2, revision 3. Revision 2 is actually deprecated, but it's just to provide you an overview. So this is the incident response model. So in revision 2, we have 3 stage or steps, if you want. The preparation phase, that's basically it's used to set the defense against potential incident, and also the threats are considered like likelihood of the impact of the threats. Then we have the part related to the detection and analytics, okay, or analysis. You detect something, you analyze this something, or you analyze the data and you detect something, okay? Then you have containment and eradication and recovery, which is basically the response. And finally, you have the post-incident activities. So it's like lesson learned where people try to blame each other. What happens? It's your fault or my fault. This has been evolved, okay? It has been evolved in part 3, in revision 3. So in this phase, the preparation is, let's say, a macro phase that has many steps: govern, identify, and protect. It's basically the same things. Important part here is that in the govern, you basically decide what's your strategy for the security. Then you identified in the identified phase what are the cybersecurity risks. And then with the protect phase, you enforce your security policy in the system. Then the other micro phase, incident response life cycle, is the one related to the automation, detect, respond, recovery. So you detect something, you have a response, you recover after the destruction, okay? This is very nice. It works for complex systems, but we have to think also about what's the target environment of this security. The 6G system. So you can see this nice picture from XX1 project, not XX2. I will not put a picture from XX2 because basically they have a number of different views of 6G system. So what's 6G? I don't know, in the sense that there's no real definition of 6G. Let me summarize this as, let's say, an evolution of 5G. So like more abstraction layers, more network segments, more tenants, multiple automation needs, pervasive security, AI everywhere, as though I presented before, 5G legacy systems, because we have to consider that we are in 6G era, so 5G is a legacy system, okay? A number of different technology. This led us to, this brings with it some security concerns. To stay in the general part, of course, potential extension of threat landscape, enhancement of attack surface, this is trivial, but my favorite is this. User can request their own services, because this is one of the promise of the modern mobile networks, okay? And when a user can request the services are also security services, okay? So forget about the SOC that decide the security for you. You can decide about your own security in 5G networks, 6G networks. But coming back to the automation, how the automation is implemented in 6G or also in 5G. They already introduced that by using control loops or closed control loops. You can see there in green. But what's the closed loop? A closed loop is a powerful key concept that enables zero-touch automation, that we can use to build zero-touch automation. So automation without any human intervention. Which kind of automation? Any kind of automation. And this includes also the security, okay? Again, though already introduced it, it consists of 3-4 stages. Here I reported another definition stream from ETSI, okay? Monitoring, analysis, decision, execution. Though was presenting observe, decide, observe, orient, decide, act, something like that. 3 or 4 stages, because you can, let's say, merge different stages like monitoring and analysis, or analysis and decision, or decision and execution. ETSI defined 4+1 stages because there is this knowledge. The knowledge is not really stage of the closed loop. It's more a synchronization point where the different stage can exchange information, retrieve configurations, and so forth, and so on and so forth. This is not a new concept, okay? Not really. It's very well known. I think that this is as old as the main kind, okay? So if this is not new, okay, because also when you try to, let's say, you try to solve a problem when there is something, an event that happens, you always apply a loop, okay? Even in the life, you always try, you are inquietant, man. Joking. You always try to, let's say, restore the systems, let's say at the original state. So this is not new. So where's the novelty here in applies closed loop in security or in general in CG networks? So the novelty is in the way we implement this loop, the way we deploy the loop, we conceive the loop. Because the closed loop are already implemented in, let's say, operators' facilities and not only, but in a static manner. They are always often part of an existing control architecture. You can see an example here. This was an old 5G project, SliceNet. I participated. This led to low flexibility, scalability, and configurability. What's the idea here? Closed loop as cloud application or cloud native application provision during the security orchestration, and where all the stage are security function completely orchestrable and configurable at runtime. So you can see the loop here, monitor, analysis, decision, execution. Imagine a monitoring phase tailored for your security service that collects data specific for your security service, like network traffic on port X, deployed wherever you want. An analytics phase that do the same, completely tailored, okay, for your security service that takes decision, or sorry, takes detect insight, extract insight from the information. Same for the decision and same for the execution. What are the advantages of this? Flexibility, of course, because this is completely tuned for your security service. And you don't need any change or slightly change in in management and orchestration architecture. It's dynamic, scalable, and movable wherever you want, and controllable, okay? Because you can manage it at runtime. Although you need specific function, closed loop coordination and governance that are defined by ETSI, the one in gray here, and they are the only part that you are going to integrate in your management or orchestration architecture. The governance is for the life cycle of the loop. The coordination is for avoiding, or let's say it's for the coordination of multiple closed loops inside the same systems. Now we have all the ingredients for this. We define the loop. We can remap the loop on the NIST IRP. Okay, and we can distinguish 3 types of security orchestration. Proactive security orchestration, where you basically establish your security solution. Reactive security orchestration, so threat anomaly detection and reaction or response to this, and predictive, which is basically the same, but use prediction instead of detection. You can see predict on top of this, of the detection phase. Where is provision the security closed loop? At the security orchestration time, when? During the proactive security orchestration. And why? Because the security closed loop is part of the security service. So this is an automation solution completely decentralized from the control architecture, wherever you want. This is defined in your security service. You can see service and closed loops in the same target environment in the bottom left. So coming to the solution provided by Robust6G, this is the zero-touch security platform we are going to implement in Robust. So as you can see, we have different orchestration service. Orchestration function. This is a functional architecture. You have the security orchestration service. Security resource orchestration that deals with the different cloud, the network security management that deals with different network service, a programmable pervasive monitoring platform, which is basically something that collects any data from anywhere. And the security closed loop management. The security closed loop management is basically that functionality I showed before. Governance and coordination, plus an interaction with the AI, because analytics stage, decision stage can be AI ML function tailored for your security solution. Okay, this is exactly what I said. Security closed loop in Robust6G. They are AI driven for anomaly detection and prediction with dynamic selection of mitigation plans. This is the final aim, okay? This is an example of use case, just to provide you a context, because we use these closed loops for, let's say, for facing strange cybersecurity threats. In this case, in use case 2, scenario 2, this is called fraudulent usage of device resources. We try to face an attack on cryptojacking, okay, where an attacker basically, when an attacker compromise IoT devices or smart devices for using their computational resource and let's say mining cryptocurrency. Okay, so we will try to, let's say, mitigate this with a couple of specific loops, or specific closed loops. This is a tailored solution for this. Well, we aim to implement this tailored solution for this use case. So how the loop is orchestrated? As I say, this is in proactive security orchestration. In Robust, we use an hybrid approach. The monitoring is provided by a specific monitoring platform that is orchestrable or configurable at runtime. The other stage are provisioned dynamically. So the security service request is the first stage. This is ingested by the security orchestrator. The security request is modeled as security SLA. Then there is the validation phase, a decomposition phase, okay, where we decompose the service in application, monitoring parameters, target environment. Everything is modeled through a specific security ontologies, and the information are stored in a knowledge graph, okay? Once everything is clear of the service, we start to enforce the configuration. Beyond the loop, there are other configurations I'm not showing here, but for the loop provisioning, basically we request the security resource orchestrator to deploy the execution and the decision. That here we are imagining as a non-AI/ML function, while the analysis is an AI/ML function. So we request a specific platform to give us a specific AI/ML application, AI/ML based application for that service, okay, for automatize that level of security. So how the loop works, I put here a couple of examples, A and B. The first is zero-touch remediation, completely zero-touch. So automation without any human intervention. So the monitoring phase collects all the information that are passed to the analysis. The analysis hopefully detect the anomaly. The decision decide what are the remediation to be enforced, and the closed loop execution asks the orchestration to enforce the security requested, the security layer requested. This is for A, same for B. There is a small variation. Here we have the human in the loop. This is because this is requested, right? AI Act in particular, Article 4, requires human oversight when AI decides on critical operations, and security is a critical operation. So instead to ask the security management and orchestration stack to enforce the security configuration, this is notified. The decision is notified to an operator that can decide to enforce the decision, if it is enforce the decision or not. This is still zero touch, is still zero touch? I think so. Let me say yes. This is because also ETSI-ZSM, Zero Touch Networks and Service Group from ETSI, basically foresee human in the loop, although they, let's say, pursue the full automation in zero touch. Here I cited a piece of ETSI 0091 where the closed loop are defined. So now we are at the conclusion. What I said, 6G system relies on different technologies and increase the complexity, and the attacks are phased. So we propose this novel automation paradigm, okay, exploiting AI-driven native closed loop that would be very effective. And the Robust 6G is trying to implement this for anomaly detection and prediction, and dynamic mitigation and plan selection. So I will leave you with just three open points as future work. First, how to deal with not security loops, because in 6G you can have different loops beyond the security. Should the closed loop management function specialized for the security? And my favorite, since the closed loop is an application, how to secure the security loop itself? Thank you. I finished.
Part of the panel where you ask questions directly after the panel. So you can sometime. And now the next presenter is Ioannis Pitsiorlas from Eurocom. And his presentation is on trustworthy intrusion detection. Ioannis, I'm just getting your presentation ready. It's in PDF, so that and control, I think. Okay, so again, arrows or clicks, and there will be signs.
Thanks. Hello, everyone. Thanks for being here. I'm going to present work that is on trustworthy intrusion detection and confidence estimation using latent space. This is a joint work between the university that I am, Eurocom, the Technology Innovation Institute in Abu Dhabi, and the University of Granada in Spain. So let's start a bit with the motivation. We know that machine learning systems make predictions with super high accuracy metrics. We see papers and papers beating the state of the art by 0.01%, let's say, and having 99% accuracy in control environments. But there are some problems with these metrics. We have a lot of false positive, big false positive rates in production intrusion detection systems. And we don't really know how confident we are about these predictions. How sure can we be about the black boxes that we just give them some data, we feed them with input data, and then we have an output prediction that we don't really know how confident we are about this prediction. And so far, current methods focus only on improving accuracy without addressing confidence estimation. But why confidence matters, especially on cybersecurity? A lot of cybersecurity teams face constantly alert fatigue from high false positive rates. And yes, critical infrastructure protection requires high confidence detection. That means that we have to make resource allocation decisions, which are going to depend on threat confidence levels, and also like the AI Act and the other regulatory compliance that increasingly demands explainable AI systems. And without confidence metrics, security teams waste a lot of resources on false alarms, and also usually they're missing critical threats. This is a screenshot I took a long time ago. It was before DeepSeek and the US elections, let's say. And let's say that we have this NVIDIA stock. We see that it's going, it increases month by month. And we have a model that says, sell all your stocks now. Would you do it? It's not easy to answer. Now it is that we know what went, but let's see another example that we have two networks, network A and network B. Network A has a likelihood of cyber attack of 70%, and network B, 90%. The question is, which network requires immediate security action? Probably we would go on network B, but if we had a confidence estimation on the likelihood of a cyber attack, we can see that probably we would go on the network A, which has a confidence estimation of 95% on the likelihood of a cyber attack. That means that confidence metrics can transform how we prioritize security responses. Yes, as I said before, so far, intrusion detection approaches suffer from high false positive rates, and they also require continuous updating for new threats that may come. On machine learning, especially with the variational autoencoders, they can play a critical role in improving the intrusion detection systems. So there is a need for a confidence metric to assess the reliability of intrusion detection systems decisions. And we are choosing variational autoencoders because they can capture complex patterns in the latent space. And thus they can help on improve the trustworthiness of anomaly detection. So yes, we need a way to measure the confidence of the prediction in order to utilize the outcome of the machine learning models. Let's start with our methodology. This is a framework of our method. We are defining a method that characterizes the trustworthiness of an unknown sample for anomaly detection before its evaluation. So given the training set and the predictor, we derive a confidence metric C, which is going to inform us about the expected error for each unknown observation. We define the expected prediction error as the absolute value of y true, the label minus the reconstruction error. And that means that we strive for a reconstruction error to be as low as possible when an instance is labeled as normal, and as high as possible when it is labeled as an anomaly. As I said, we use variational autoencoders, which they consist of an encoder network and a decoder network. And these are some notations. And the encoder approximates the posterior distribution, and then the decoder reconstructs the input data from the latent representation. The objective on variational autoencoders is to maximize the elbow or minimize the negative elbow, and also to minimize the reconstruction error and find the balance between the reconstruction and the KL loss. We also use the Mahalanobis distance. This is the formula. Here the X is the latent representation of an observation. Nu is the mean vector of the training latent representations, Z-train, and the sigma is the covariance matrix of Z-train. What's interesting with the Mahalanobis distance is that it adjusts for data distributions by considering the covariance of latent representations, and thus it normalizes distances based on variance and feature correlation. And then it scales them according to the data spread. How we calculate our confidence metric is that first we train our model, the variational autoencoder, in order to get the representations, the latent representations for the training data and for the unknown data, the inference data. And what we do is that we consider that the unknown observations which are closer to the representations of the training points in the latent space regarding always the Mahalanobis distance are more trustworthy. So we want the inference data to be as close as possible on the latent space with the training data. This is how the formula translates for our distance metric. And we evaluate this metric in order to be informative with the error. So we measure the correlation with the prediction error, which, as I said, it's the true label minus the reconstruction error. So this is the correlation with our metric. In this work, we use the NSL-KDD dataset, which is a very well known for scientific purposes dataset. We focused on binary classification. We have not yet gone to multi-class classification. So as you can see, it's a pretty balanced dataset with normal traffic and intrusions. And the features of this dataset are basic connection details and some traffic flow information. Our variational autoencoder consists of this, the encoder and the decoder that has all of the layers are followed by the ReLU activation function. We are working on an unsupervised learning setting. Here in the figures, you can see the projection on the latent space of the training and the inference and the test data. And for the results, we had to adjust the model parameters, and the key parameters are the latent space dimension and the beta parameter. We treated this problem as a multivariate problem and tried to solve it via alternating optimization, so one parameter at a time. The latent space dimension, you can see some of them. We tried much more dimensions, and we found out that actually having a latent space dimension of 20 gave us a pretty good correlation on our confidence metric, 42%. And then we checked by having the latent space dimension as 20, the beta parameter. And starting of a smaller beta parameters, we found out that actually having it 0.25, it increased the correlation to 45%. That means that higher beta values that we tried led to decreased in correlation and model effectiveness. And the trade-off here is that it balances computational complexity with the model's ability to capture meaningful patterns. We also had to find the optimal threshold for the reconstruction error, and that we did it by trying to maximize the F1 score on the training data and having the model settings that we found before, latent space 20 and beta as 0.25. We found out that the optimal threshold here is 0.07. And these are some evaluation metrics that we had to have. The correlation analysis of our confidence metric, you can see that we had pretty good correlation on false positives and smaller correlation on false negatives, true positives, and true negatives. And also we evaluated the distance metric. We didn't try only the Mahalanobis distance, which helps to account for covariance structure, and it's pretty effective in detecting anomalies. We also tried the Euclidean distance, which is simpler, but it proved to be less accurate because it doesn't consider how the data distributes. And we also tried the cosine distance, the cosine similarity metric, which measures vector angles, and it's useful in high dimensional spaces, but it was less effective here. As you can see, the correlation was 45 with the Mahalanobis distance, 38 of the Euclidean, and the cosine similarity had 32. Also, the Mahalanobis distance helped a lot with as we decided that we're going to use this distance, then we tried to figure out the computational complexity. So we tried the latent space, which was a smaller dimension because the compressions of the variational autoencoder, we had it as 20. So the covariance matrix computation, which the Mahalanobis needs to do, is less demanding, and we had an execution of around 8 minutes. Well, when we tried the same with the feature space, since it's the original dimension of the data, the covariance estimation was very expensive computationally because of the matrix inversion. So we had a slower execution around 37 minutes. So latent space proved to offer also meaningful embeddings and enhanced computational efficiency. Right now, we're extending this work on agentic AI. So we have a setting of a collaborative multi-tenant network automation. So we have LLM-based agents for tenant negotiations, and the LLM arbitrates the incoming messages by classifying the reasoning as malicious or benevolent. So it's threat or no threat, actually. And we estimate the confidence of the reasoning classification by integrating our method. So to conclude this, we address the need for confidence and trustworthiness in machine learning predictions, in anomaly detection or threat detection, classification, or regression problems. And we highlighted that the distances in latent space derived from variational autoencoders are more than mere numerical values and can bear significant implications for the prediction confidence. We showed that the proposed methodology shows a new potential in general for the use of latent spaces, not only for dimensionality reduction, but also as a cornerstone for trustworthiness in AI. And we proved that variational autoencoders offer a novel approach for improving intrusion detection systems, confidence estimation against sophisticated cyber attacks. That's all from me.
That is after the coffee break, our part of the panel, so we can take questions later. And Betul is already jumping out to join the stage. So I'll prepare the presentation here. So Betul is part of the Robust 6G project, and she is working in the Ericsson team. And her presentation is going to be on robust intrusion detection systems. So the right arrow or the click.
Okay, thank you. Hello, everyone. My name is Betül. As Bart told you already, I have been working for Ericsson. Maybe it has been approximately 3 years. And I have been working as a researcher. And this is my first time in Dublin, and I like the weather. And today, I'm going to talk about robust intrusion detection systems. Again, similar topic that previous speakers mentioned. But I will mainly give the motivation, background, and why we need robust intrusion detection systems. And I will also connect our study focus in Ericsson research, and also connect explainability, as it is common, like current hype. And I would like to start with the need for trustworthy AI ML for 6G feature networks, and why we need trustworthy AI ML. We assume that 6G will be data-driven and also multi-vendor, multi-domain, multi-stakeholder, multi-everything. So we need to provide trust between all these components. And when we say future networks, specifically 6G, I would, in my view, the main difference between the previous ones would be AI ML utilization. It's really important for 6G for integrating AI ML, and this could be for optimization, cost reduction, network management. But what we are focusing is specifically for robust and resilient systems. And for robust and resilient systems, we also need to secure our networks, users, etc., for against cyber attacks. But there is a trade-off there, because when you use AI ML, there is a possibility that your AI ML model could be vulnerable to some attacks. So this could affect your system. And to be able to prevent this attack type, we need kind of better utilization of AI ML. So we need to make sure that how we are approaching AI ML models. And I would like to just give a brief introduction about intrusion detection systems, but you already heard some of them. But we mainly need intrusion detection system specifically for 6G networks or networks to safeguard, protect our networks against cybersecurity threats. So with these systems, we can monitor the system networks, events, and detect what's going on, like kind of suspicious network incidents. And then we can also alert the system or technicians to incident responders. And then also we can give the response. So the best approach for intrusion detection systems, of course, kind of proactive defense system. So we can identify threats before happening and take reaction, and we could decrease the attack numbers. So for these intrusion detection systems, there are different ways that I will mention later. But when I say intrusion detection systems, actually there are different kind of intrusion detection systems, but what we are focusing here is network intrusion systems. So there is specifically, there is a setup at a planned point within the network, and we can examine the traffic from all devices connected to the network and perform like observation of traffic. So as I said, there are different types of detection methods that we call it misuse versus anomaly. So what we call misuse is signature-based methods that we can also consider them as rule-based. And this kind of detection approaches detects the attacks based on specific patterns of the some features like a number of bytes or a number of ones or a number of zeros, etc. But what we are interested in our approach is mainly anomaly-based methods, anomaly-based intrusion detection systems. So in this case, we can, like if we introduce an anomaly-based detection approach, we can detect unknown attacks, like as new threat coming up, we can understand the new threat. So this is the main difference that differentiate the signature-based and the anomaly-based, so which is mainly like the current approach, I will say. But there is, of course, some approaches both connects like signature-based and anomaly-based methods, etc. And like I'm saying intrusion detection systems, but what I mean actually is intrusion prevention systems. So there is just a slight difference between them, and sometimes the meanings are mixed off, but in intrusion prevention systems, this is kind of proactive approach. So before new threats coming, we can analyze and we can guess, predict whether what kind of attack we are expecting, and before attack happens, we can like proactively eliminate it and detect it. And machine learning is is seriously used approach for intrusion detection systems for specifically anomaly-based detections. And with machine learning, we can learn the function mapping, and we can discriminate whether the input, the traffic is benign or not. And there are dedicated anomaly detection algorithms for this reason. And there are also supervised approaches for like intrusion detection systems such as deep neural network, random forest, etc. But the main concern here, without considering any approach, like intrusion detection systems should be able to understand what is the normal and what is the benign in your network. And you already seen this. Autoencoders are the main method, ML method for anomaly detection, widely used for several systems, and the results are also really good when you use autoencoders, which basically a neural network model encodes the data, then decodes the data one more time, and understand whether your input is malicious or not. But there are some kind of difficulties of these intrusion detection systems. The first one is the data problem, and the availability of data is kind of tricky to get the data. And this, if you even get this data, you need pre-processing, which is really not good. And also there are a high number of false positives. Like ML approaches are mainly a good approach, good solution for to deal with these false positives. But on the other hand, there is still like improper approaches for signature-based, but anomaly-based approaches are still imperfect. And if you are using the ML-based approach, there is possibility that if attacker has classifier model or some kind of information about your input, that means the attacker adversary can create attacks that can evade the detection, which is the topic of today's presentation. And I was telling that trustworthy AI is needed for 6G. And if you consider IDS is one of the main components of IDS, 6G, then it's supposed to be trustworthy as well. Yes, AI ML is a very useful tool. We can use it in very different domains, but there is also proven that like AI ML, specifically some complex black box ML models are vulnerable to adversarial attacks. So that's why we need robust AI ML approaches against security attacks. And then at the end, we can like provide a robust intrusion detection system. So we want to provide like at least protect our AI ML approaches. And at the end, we can have more trust in our intrusion detection systems. If we could increase our trust, that means we could also increase the trust to network. And our focus is for this topic to provide adversarial threat detection. And the problem is there is IDS, yes, it's ML based, but it might be vulnerable to some other AI ML based attacks. And we want to develop some techniques that can detect these adversarial threats. And what we use for this kind of problem, we utilize explainability. What we know that explainability is very common for transparency reasons, but in our case, we use explainability to detect adversarial attacks against AI ML models. And we suggest that the combination of traditional approaches and AI-specific security measures are the best ones. And we would like to monitor the network continuously so we can adjust and detect new threats. And just a quick recap here. I guess some presenter already mentioned that there are some security and privacy threats to AI ML models. For example, for the security attacks, data poisoning, evasion attacks are one of the widely used ones. For the privacy, membership inference maybe is one of the common one. But here, when you want to provide security and privacy, there is kind of a trade-off as well, which needs to be considered. And the limitation of ML framework actually comes from the boundaries of the our ML model, which can be easily manipulated. So, for example, just a short, example, like when we have, if we go over image recognition, when we have a van image, our model, if it is manipulated, it can predict our van as dog, but at the end, we can still consider that this is true classification. So we manipulate the model at the end. But if we come back to IDS problem, here the problem is more more specific, like that there is already IDS problem. So there are some kind of attacks that could be signaling storms or DDoS attacks to network, and our IDS is supposed to detect these kind of attacks. But when there is also adversarial attack to our intrusion detection system, adversary have more power on our system. So our intrusion detection system will not be able to detect new attacks. So like the attacker on the network side will be more powerful, successful as well. And we want to solve this problem. And then there are some state-of-the-art approaches for this kind of problems that you can use adversarial training, which is also widely a common approach, or denoising autoencoder. If you are using autoencoder for IDS, so you can input, you can include some kind of noise into the autoencoder, and your autoencoder learns what is noise and what is malicious, etc. But the thing is, these solutions have kind of efficiency problems. For example, if you consider adversarial training, you need to it brings complexity. So you need to intervene the training part, and this brings some computational inefficiency and also lack of transparency. And we want to solve these problems. And that's why we include explainability. So I'm sure you already have some information about explainability, kind of user trust, model trust it brings. And it can also improve the model. And that's why we want to use explainability to provide security for intrusion detection systems. And for this reason, our studies include, we have different studies for this reason, for this problem. And what the main contribution here that we use explainability, not for transparency, but for detect adversarial attack. And we can also, we are able to also do this in real time. This part is important because what we want to is monitor the network real time. And then there are different approaches that we develop, but you can check the papers. And I would like to come back to a conclusion to be faster. So we are addressing both transparency and security problems simultaneously for our studies. And what I would like to say is we don't need complex models or heavy models. We can combine both rule-based and easy algorithms, maybe even white box models, and then have good performance. So we don't have to go always the complex black box, highly heavy deep learning models. And our approaches also require dynamic adaptability, real-time attack detection, which is also really main concerns. And the thing is, there are still new threats, attacks that are being developed, and it's really hard to follow each attack types. So that's why we need proactive intrusion detection systems. So it should be real-time, adaptable. So not kind of intrusion detection, but intrusion prevention systems. And what we are talking about is 6G. We expect large-scale networks. So this kind of deployments should be able to also adapt for the real-time and very large scale networks. And that's all. Thank you for listening me.
Also,
Mhm.
so any questions we can leave later. Now we have the last talk before the panel. So from University of Murcia, we have Jose Maria. I will find your presentation. Of course. Check if it works. Yeah, okay, perfect. Okay, stage is yours.
So, good afternoon, everybody. First thing that I would like to say is that I'm the last one before having lunch, so that's good news for you. I would like to start my presentation by ask you a question. What technology are key for you for the next 6G network? Some keywords, ideas in the audience. AI, that's true. Nothing else. Quantum, maybe. Okay, so, well, this is one of the, let's say, visions that we may have that is coming from Nokia Bell Labs, that is the lead of XIX1 and XIX2 project. They are the flagship project working on 6G network, even though, as Pietro said, we don't know what is going to be 6G, probably an evolution of 5G, I agree. But mainly, one of the main aspects that 6G will bring is new requirements. So requirements in terms of design, in terms of development, and of course, we need to connect and to be smarter than we are right now. So for example, one of the requirements that we will have if interconnected devices, we plan to have billions of devices connected, lower latency, end-to-end connections. So normally those requirements that are related with the performance, they are associated in some way with what we call service level agreement. That is basically a template in which we may declare all those requirements, and then during an ongoing relationship, we will check if those requirements are being fulfilled or not. An example in which we may see, even though it is not really good depicted here, is what is a marketplace, but basically it's a paradigm or ecosystem in which we have consumer and providers are in charge of registering those services or resources that they are not going to use, and consumer, they are interested in consuming in order to cover certain peak of loads that they may have on real time. So basically, consumers and provider establish a business relationship, and they will sign an SLA in which those technical requirements are declared. But there are also requirements in terms of, for example, cross-domain and multi-stakeholder characteristics that basically means that in an end-to-end connection, we may have multiple providers who belong to different administrative domains, and we need to determine if both providers have the same capabilities in terms of sources, computation, storage. What path do we select in this scenario, for example? And here it is when the trustworthiness may help us to bridge the gap. But we saw many ways to define trust. So we may see trust as a explainability on AI models. We may see trust if we are using, for example, hardware as use enclave that basically is isolated areas in which the attacker cannot enter, and we have deployed actions there. And in this case, I would like to present trust as a human. That basically means, as humans, when we trust someone, it's based on the historical data or the reputation that that person has with us. So basically, we observe quantitative parameters or qualitative, depending if we want to receive feedback from third parties, and we can establish trust links between the different, let's say, people that who we are interested on them. Of course, those parameters can also help us to detect some deviations or breaches and stop our relationship. Other characteristics regarding reputation could be that, for example, we are not a one-time process. It is not it's a continuing process that we monitor at the beginning, but also during an establishment. And as we will see in the next slide, we pursue trust as an intent in order to orchestrate the network. So talking about trust and reputation model, this is a high level overview. So my idea here is just to, let's say, show the main models that we may have, regardless of the enforcement scenario in which we want to apply the trust models. That first of all, we have the information gathering that basically is to collect raw data. We may deploy in IoT environment. We may deploy in a RAN radio access network, or even in the core of let's say, network like 5G. Then all those raw data are passed to the computation model, and here we may apply different techniques. It really depends on the requirements that we have. If we have information enough, we perfectly can apply machine learning or deep learning models. But sometimes we don't have information, or even we need to provide those information to create our model. So in that case, we may take advantage of statistical models, or even create our personal, let's say, customized algorithms. Then all this information is passed to the trust storage model, when we may determine, based on the privacy or the scenario again, if we want to use private database, public repositories, DLTs, or even data lakes. And finally, the last one is, as I said, we are not one-time process. We need continuously to update the trust score. So we need to see other events that may happen, like security incidents, the pass of the time, or some breaches in, let's say, a smart contract, for example, that may take into account and adapt the initial trust score. So now I would like to present two scenarios in which this trust model has been applied. The first one comes from 5G Zorro. As Pietro is looking at me, it's one of the previous projects in some colleagues we were working together. Basically here, the idea is that, okay, we have a set of product offers that basically means potential providers that we are going to use. And we need to determine what products and what provider are, let's say, more reliable. So in that case, we need to extend a slice in order to continue a streaming service. Basically, what we do is to determine the trust score using previous interaction, using historical data, using security events, the number of products, the number of relationships, and based on that, we compute a trust score. As we may see in the plot on the right-hand side, that framework didn't introduce delay in the overall system. Basically, when we receive more than 6,400 events, we only require almost 1 second. So we didn't, let's say, create an impact on other services running. Something similar happened also with the performance. In the system or in the server in which we were working together with other colleagues, we only consume 12% of memory and 2%, sorry, the CPU, and an insignificant amount of memory. So what is good news, that basically means that trust can be combined with other existing technologies. But as many of the, let's say, presentations that we had today, trust also suffers some attacks. So we need to create countermeasures, and we need to be resilient. In this case, we launched certain attacks like padmouthing, for example, also on-off attacks, or circulation attacks. And this in particular showcase how, when we have bad recommenders in a population that we need to select good recommenders in order to get feedback, we were able to determine when we have a 30% of malicious recommender, the good one, we selected the good one with a 97% of accuracy. And the impact that we have in our system was only the decreasement. We decreased the trust score in 2 points. So what this basically means that we are resilient and we don't have a huge impact on the reputation calculated previously. Another example is under the XIX2 project, that is one of the 6G flagship projects. And here there is a use case called it transparent notary service, that basically the idea is we have a level of trust assessment function, that is the trust model. Now we are using performance-based approach. So we are not going to use the transaction. We are going to check the performance in real time. And all those data are going to be pushed to the transparent service that is a distributed ledger technology. Why? Because in that way, we may guarantee that auditors can check if we fulfill or not what we agree in a contract, but also other consumers who are interested in creating new relationship may get feedback from a transparent service. So, sorry. In order to compose, let's say, the trust model, we need to fulfill two main objectives. First of all, to represent the information. In this scenario, is contextualized under the cloud continuum environment. That basically means that in a relationship, we may have different resources coming from the edge until the cloud. And we need to combine all those resources and guarantee a seamless connection. So we didn't find an ontology that may match cloud continuum concept plus trust management concept plus intent-based solution. It is true that intent-based, there are plenty of ontologies and knowledge representation on that. And that's the reason we use, let's say, software use approach. That basically means include those classes that already exist in an ontology in our approach. The ontology as well as the interpreter, because we create an interpreter in order to get the intents and then pass to the monitoring agent to configure the tool and monitor in real time those data, are available in the link below. The second part is regarding the monitoring activity. We develop a monitoring agent using a standard, but basically the idea is to check the service assurance of different resources. The agent per se can be applied on physical or virtual devices, and we have a list of predefined rules. Based on the requirements that we get from the interpreter, we activate or deactivate the rules in order to fulfill the trust requirements using basically BERT and LLM models. And now we are working on adding new rules in real time when we don't have policies or rule enough in order to check what user may write during the first phases of an intent-based network solution. So that's more or less all from my side. I would like to conclude saying that the research topic that we see under, let's say, the trust paradigm, that basically is to taking into account the new scenarios that appear under 6G network, like the cloud continuum, because there are plenty of requirements, not only in terms of performance, but also in terms of design and development. That means that previous model need to be adapted. We don't need to, let's say, start from scratch, but we need to adjust what we have. Also, we envision and we pursue trust as a new intent for orchestrating network. And that's the reason why we are trying to define trust level agreement that is a subtype of service level agreement, but oriented to the trust requirements. So who we are, because I didn't present me at the beginning, where I belong to the Cybersecurity and Data Science Lab that is from the University of Murcia. We are working on trust aspect more than 15 years. And this is the team to which I belong. We are 50 each people, of course, led by different associate professor, full professor, and with the help of postdoctoral students. We have mainly 8 research areas in which we are working on. In my case, I belong to the security and trust, let's say, topic, but we have a really close collaboration with the other areas. And in fact, we will be here covering a couple of them, like the AI and trust for robust SG. That's all from my side. Thank you. Yeah.
So the panel will be led and moderated by Dr. Pasca Olivera. So please come in. So I'll ask all the presenters, Ioannis, hi. Joel. I only have one. Test.
You can give it to them, right?
Yes,
I use this. I
you can use
stay here.
this.
Yeah, I
and
can stay here.
They have to pass this around.
Yeah, yeah. This, oh, yeah, you know.
So whoever comes first, you need to give that.
Yes, yeah.
Thank you for that person.
Sit close at me.
Lima mein.
Yeah.
What do you want to do?
No, no, I was checking whether camera can be used there.
As long as.
So, Pathika will present first from here, right? Yeah.
All right.
Yeah, yeah. Yeah.
So you have the first presentation, sir?
Yeah.
Which one you want?
Yeah, yeah, never. Okay. Hello, everyone. So I'm Pasika, and I'm representing UCD. I'm an assistant professor here, and basically, I will be the moderator for you for the first panel on securing the AI-driven 6G networks from architecture to autonomous management. So in this panel, basically, we have 4 experts. So we will try to discuss how are the research areas that these 4 talks or 4 research people has like discussed is going to like help deployment of 6G networks further on with AI-driven abilities. And so first of all, I will introduce the panelists. So basically we have Pietro, which is sitting like closer to me. Pietro Giardina. So basically he's a deputy technology lead from Networks R&D. And first of all, if I make like any mistakes regarding like pronouncing your names, please excuse me. I will try my best. And also the companies, yeah. So it should be Nextworks, is it? Yeah.
Nextworks.
Hopefully, yeah. Right. So he's an expert in network orchestration, AI-driven security, and UKD. So if there's something to do with zero-touch security or automation, Pietro is the guy. So basically, he's an active contributor to multiple EU-funded research projects, and most of them is like developing this ICT-based solutions. So thank you, Pietro. And secondly, we have Jonas. So it's Pizzarolls, hopefully. Yeah, close, at least. So he's from Sorbonne University and also Eurocom, representing here. And his research areas are trustworthy AI and confidence estimation in intrusion detection. If you have listened to his talk, so you've realized that. So so basically, so his background is on data science and semantic communications using deep generative models. So thank you for being here, Eunice. So and also Betül Paltun. So she's a senior researcher from Ericsson, Turkey, and she's experienced in AI security research at Ericsson, Turkey, and also
she's working on adversarial robustness, transparency, and resilience idea systems. So thank you, Betul, for being here, and also Jose Maria. So representing University of Murcia, Spain, and he's a senior researcher there. And basically, he's working on cross-domain trust management for beyond 5G scenarios. So that is your, thank you, Jose Maria, and this is basically our panel. So next, we'll actually like walk through what would be the outline the schedule look like. So I will have some opening remarks, like where I will just introduce certain background information just to follow through this panel discussion. Then I will do I will lead a Q&A session. Like basically I will ask certain questions from the panel, and panel will hopefully give me answers. So I'll promise to be the questions hopefully to be like easy and plain as far as I'm concerned. So also afterwards I will open the session to the audience, where audience can ask questions not only about this panel but about the talks that they have done earlier. Then we'll have a kind of like concluding remarks at the end, hopefully. And timing is just basically like indicative only. So hopefully we can hour up and go for lunch early, hopefully. Let's see. Okay, so opening remarks. So this section, basically I've used this to introduce what we are talking about. So mainly it's about 6G. So I believe like you heard of 6G a lot. And basically you will hear about it in the latter stages as well. So the aim of GT is to enable intelligent, ultra-reliable, low-latency communication through pervasive AI. So basically AI being the keyword there. And in comparison, it's basically integrating AI ML to enhance the adaptability and capability of services. So that's the idea. And so just to get an idea of how this is relevant. So all of you know that 5G is in deployment in some places now, and it's actually like supporting massive IoT and like energy efficiency, edge computing, network slicing, and all these keywords that coming into picture with 5G. But the problem with 5G is that so the applications that are actually promising, like digital twins, like remote access surgeries and all those, actually need much better sort of infrastructure, or maybe kind of like a more better solution. So that's why, since AI is kind of like expanding horizons at the moment in the industry and in research and everywhere. So why not use AI to enhance 6G or other current networking infrastructure and try to optimize this further and like improve the service flow. So that would be one of the like key elements of 6G AI mainly. And of course, there are other aspects like quantum communications and other aspects. But our main target for this panel would be AI. And so also, what would be like, we have AI solutions, of course. We can like have typical like standalone AI solutions, but how to integrate all of that and how to manage that. So AI-driven autonomous management in 6G is kind of like a challenge. And also like typically AI services, when it becomes autonomous, we have to think about decentralization and how to like expand the service infrastructure into decentralized locations. And while doing that, how to manage the security and what comes arise through privacy issues. So how to find solutions for that, and what would be the like solutions for the attacks that are targeted for the AI intently. So those will be the kind of things that like researchers will be looking into at the moment. And so just I'm gonna give a consider like a is it not? Correct. So basically, I'm going to give some background like knowledge on zero touch integration. So basically, from the user devices to the core network. So you have the radio access network or the Open RAN, right? Then you have the edge and the core, where our core basically can be the networking infrastructure or the let's say 6G core, or it could be like core kind of like cloud, where the application is hosted. So between the device and this, so the entire network flow should be automated for security, right? So this panel is about focusing on security aspects and so observing, analysis, and acting and decide. So that will be the concepts of zero touch automation. So that like basically automating all these aspects through the end-to-end security tunnel would be the idea of automated security in 6G. And of course, there were like intrusion detection systems came into picture. So traditional IDSs are more or less rule-based and somewhat signature-based, policy-based, operational, but that is not enough for 6G. So we need to integrate AI, but by doing that, what would be the challenges? So basically, AI-driven intrusion detection systems is a kind of like a pervasive idea in 6G, and that's also we will be talking about. And then SSI and DID. So DID is basically a global unique identifier, which we call as distributed IDs. And so using that, we can actually like ensure the security and privacy of communication and entities throughout a decentralized environment. So SSI or self-sovereign identity is kind of like a model that uses DID. So this is something that we use with blockchain and DLT technologies. So these are the things that we will be discussing during this conversation. So just to give you a brief understanding of this. Okay, so the boring stuff is done. So I'm just moving on to the important stuff, hopefully. So this session, I will ask questions from like the panelists. So first off, the first question is directed to Pietro. Yeah, so basically, one of the key pillars of AI is like AI-driven 6G networks is automation, right? Typically. So, in 5G, which is in deployment now, it's basically partial automation that we have. It's not complete automation, right? So when you have that kind of infrastructure and try to, like have 6G, which we need to have which demands zero-touch security, autonomous running across diverse domains and all that. So how would your work, right? So how would your work on orchestration and automation, so would when you are trying to integrate that in 6G, what would be the major challenges that you will come across?
Well, yes, thanks for the question. Well, actually, there is a number of technical challenges in doing this, especially for enforcing, let's say, automation. I think that the key problem is probably the heterogeneity of the different of the technologies that we are going to orchestrate in the sense of the security and the automation that we are going to provide there. Well, heterogeneity, it is not only for the technology, but there is also, I think, a human factor. But staying on the technology, let me say that it is very difficult to, let's say, try to orchestrate a security solution that is, let's say, effective for this, let's say, complex environment. For example, we proposed these automations based on closed loops that they are adaptive, so they adapt to the different technologies, okay? But for example, how to deploy them? How many of them we can deploy, for example? Is it sustainable? Who is going to provide the AI, for example? Okay. my favorite, the one that I expressed at the end of the talk. We would like to provide this automation solution as a cloud native application, but this our security solution should be secured itself. Okay, so those are example of technical difficulties that we can face in this kind of deployments. And well, let me cite also the human factor, because when we discuss different technology domains, okay, we are not considering that these technology domains can be also different administrative domains. So this adds complexity, especially because when you put the business in the middle, okay, everything suddenly becomes more complex, okay? This is another factor. The other human factor is that in the solution we proposed, we need basically software engineer that are also expert in security. So the lack of skill the lack of skills is another important factor, because security experts in the defense, I mean, are usually IT guys, sysadministrator. They have, let's say, no deep knowledge about programming. So this is something that should be considered when basically we create security groups and try to deploy this kind of solution in a complex environment like 6G.
Thank you, Pietro. Thank you for that answer. Just to build upon that point, and also like considering, 6G is always decentralized, and at least it's intended to be decentralized, and that makes it the reaction time, it's much more critical, right? So building on that, so let me, where's the presentation? Is it not visible?
It disappeared.
I was like looking for the presentation, but yeah. Maybe. Second question. Yeah. Okay. So the camera is okay. All right, great. So building on that, so can you see this?
Yes.
Too far?
Yes.
Yeah.
No, it's okay.
Yeah.
I can see it.
Yeah. So building on that, so basically like decentralization and meaning like reaction time for that becoming critical, and so all these aspects come into the one word called orchestration, right? So how do we design an orchestration framework, that would be more effective to like launch these ZTA based or ZTS based solutions?
Well, the question is also reacting in real time, right?
Yeah, reacting. That should be there.
Yes, because that was, yeah. Well, the trivial answer will be that when we think about unknown threats, trivial answer is that this orchestration framework should be able, I'm not saying to identify, but at least detect this unknown. So this non-ordinary behavior. Okay, no, in words it's easy to say, okay? But I guess that this can pass through a collaboration between, let's say, human and AI, okay? The fact that 6G is AI native, it is important because humans are somehow able to identify something strange, although they don't know what is happening, okay? So we feel that there is something that is not going well, okay? And probably we can train AI in this sense. At least, I will say, to try to identify that there is something that is not going well. Then, as human, for example, we investigate the unknown and assimilate it. This is the way we learn. And we should do this also with AI-driven solution. Okay? This could be one way to proceed. I cannot guarantee that this can be effective in real time, okay? because of course we have a learning process first. Mhm. But definitely it can help us providing a prompt reaction in this sense. So collaboration, human and AI, or let's say AI-driven automation system.
So, like, in your opinion, just to get
Yeah.
an opinion on you, so there are various aspects to orchestration, like with AI, and so with AI, like what aspects do you think that you can improve, or rather, what would be the most challenging aspects of orchestration?
Well, of course, if you would like to orchestrate promptly something, you need dedicated platform for this. Okay, so this platform should be, let's say, dedicated to produce AI for mobile network in general, but for security in our cases. Okay, and they should offer interfaces for this, for promptly selecting models, retrain. From the orchestration perspective, we should have the possibility to ask, okay, I need a new model, please train this with this data, because I need this for security. Okay, so we need this kind of platform, probably.
Thank you, Pietro. Yeah. So, presentation, yeah. Thanks. Yeah. So, next question is for Eunice. So, okay, so when we think about when we like integrate AI, right, and like AI making decisions and all that. So, from your like the talk, so the confidence becomes kind of like very important for accuracy, right? So for the overall process when AI is there, and so if we kind of like estimate how the system is, so and to make decisions that is well risk informed, and in that case, so with your expertise on like latent space representations in AI models and all that, so can you elaborate on how these matrices can be used to enhance the trustworthiness of a typical AI system that would be integrated into 6G, let's say?
Yeah, so thanks for the question. We need to understand that by having, for example, a variational autoencoder and projecting the data into another space and not only having the original dimension of the data, but also having the latent space, which the data that are projected there are compressed and they have some information in this compressed space. So the idea of measuring the proximity of the new inference data that comes in our model and measuring the proximity to the already trained and learned data, this can mean something. And we found out that, for example, this is a measure of confidence, and the closer they are to the already trained data, the more confident we are about if it is a threat or not, or whatever. It's not only on threat detection, it can be on whatever, on 6G as well. If we have an application on that, we can apply this method. So latent space is something that we don't really understand, but we're exploring it, and it's a topological area, let's say. So if we measure these distances, they mean something. Yeah.
Right. Thank you, Ernest. Okay, so okay, let's say we have a next one. Yeah, next question. Yeah. So if we have a kind of like a large scale 6G environment, right? So if we have like more like false alarms, false positives and all that in that environment, so it can actually overwhelm the response systems, obviously, right? So in that scenario, in your perspective, like how can like AI-based IDSs can adapt to this kind of scenario in a large scale environment, with like a lot of false positives, like how we can like overcome that.
Yes, okay. Give me a sec.
Yeah. How can IDS adapt effectively to dynamic threats while maintaining low false
So-
or positive rates?
Of course, for sure, when we have a large environment, let's say, a lot of new attacks might occur and happen. So then we speak in terms of concept drifting. So we need to have models that they can adapt to new attacks and threats. So one step that we can do is, of course, use semi-supervised or unsupervised learning for our models, so they don't rely only on what they have seen. And in order to reduce the false positives, something that could happen is to adapt how sensitive the model is on how it classifies the new instances. So, for example, if we are too sensitive, then for sure we will have a lot of false positives, but this is where metrics like confidence and explainability come, and they can help us be more sure about which attacks are more threatening than others. Yeah.
Yeah. So you need kind of like quantify like threats and try to approach that.
Yes.
Okay, right. Thanks.
Thank you.
Yeah. So I'll go to Betul for the next question. Yeah. So I mean, AI is not just a defender, right? So I mean, it can be attacked as well. So we've seen it obviously, and we were researching about it now. And one of them would be like adversarial attacks, like so, if you know some like resourceful like attacker who can do this kind of adversarial attacks. So, right from your like basically perspective, Betul, so what specific vulnerabilities like concern you most? Like basically, what makes IDSs vulnerable to adversarial attacks in 68 environments? But of course, there could be plenty. But what would be the main like threats?
Thanks, Pasika, for the question. If we consider 6G environments, maybe I will say the heterogeneity of technology. So as we expect in 6G environments, there might be several different technologies that we need to integrate. That could be quantum computing, blockchain, IoT, etc. So all these technologies can bring their AI, their own AI approaches, models, etc. So in this kind of distributed and very large scale environments, we need to find a way how to handle all these AI models at the same time, because they all coming from different approaches, technologies, etc. So this would be the main concern here, I would say. But to handle this situation, maybe monitoring all the network, real-time applicability would be one of the important tasks of 6G environment, especially if we want to keep like IDS, intrusion detection systems, in a secure way. But here, for example, for different technologies, we would have different IDS, but there is also we mentioned massive number of data. This is also a big concern, like how to handle efficiently all this data if we want to keep our, if we want to protect our intrusion detection systems. And we also consider real-time monitoring monitoring these environments, networks, technologies to keep our IDS safe. But here there is another concern, such as when you like monitor, observe the network real time, continuously, this brings another problem, such as privacy, because you need to like investigate everyone's data, monitor them in real time, and what happens if a user do not give the consent for this reason. So here I would say security and privacy should be considered at the same time in a large scale environments. But when we talk about the components of trustworthy AI, and there are some trade-offs, such as between security and privacy. You want to protect the security, but also you leak or you give you open some vulnerabilities on the privacy side. So you need to handle this trade-off. Or, for example, in terms of explainability, you want to provide explanations to the user, like operations, operation personnel, etc. But that also opens a security and privacy problem as well. So I guess all trustworthy components should be considered at the same time for a like robust systems in 6G environments.
Okay, so it's like by design, all the security and privacy aspects should be considered so that adversarial type attack can be. Yeah, that's really good. Thanks, Betul. And since you mentioned about like real-time monitoring and all that, so basically, I mean, with AI, it's given that you have to have a system with real-time monitoring and which is not static and it's evolving over time and like doing self-learning, self-healing aspects. So, but the problem is how to like maintain trust in a model that is not static, like which is dynamic all the time. Like how can we like establish stuff? So what are the things that we could do, like the best practices that we can maintain the trust in a dynamic 6G environment if we, of course, like integrate AI in 6G? What should we think?
I think this is kind of tricky question, and maybe the first thing will be human in the loop, and Pietro might not be happy with that since we are working on zero-touch automation systems. But what I mean by human in the loop is kind of like involve human intervention, but not the mean as we guess. For example, not the direct interaction to operation systems or AI model even. Here what comes is transparency. So if we want to build such kind of systems, and if we want to continuously monitor, adapt our models, it is supposed to be transparent. So if we understand what AI model does there, what kind of operations happening, that could give us a trust on the systems that we are using. This is the I guess like main components of this kind of systems. And I also believe that this is also important for AI regulations. So yes, I would say let's keep human in the loop, but in terms of transparency maybe. And this also gets the kind of AI, it also gives ability to provide AI governance. So the other thing is, for example, we are saying real-time applicability, continuously adapting, but here there is another challenge, again, privacy issues. So we also need to provide privacy if we want to monitor all the network data real-time, continuously. So we should be able to also provide privacy at the same time with security. This comes to same answer as the previous one. So maybe distributed systems would be really important if we are considering like real-time continuous monitoring. That could be the one of the main answer, I guess. Privacy is the main concern. Like users, operators, vendors are like kind of afraid of.
Thanks, Phil.
Thank you.
So, yeah. So next question is for Jose Maria. So Okay, so the decentralization is like a thing that I mentioned like few times now for 60 environments, and it's one of the things that with decentralization that all kinds of service providers, operators, subscribers, everyone has to like have a kind of like trusted environment in this kind of environment. So in order to like guarantee this kind of a trusted environment without prior relationships, so how does reputation-based systems can play a role in this scenario, according to the research that you have done?
Okay, thank you for the question, Basika. Well, one of the ideas that came to my mind is like, for example, normally catalog, one of the ideas is to concentrate resources coming from decentralized parties or decentralized operator or stakeholders. So, for example, not reputation-based models can help, but any other trust model that we may apply also is because at the end we are introducing a new dimension that can be taken into account when end users or stakeholders need to take decisions. If you need to hire specific resources, 8 years ago, basically you declare requirements or intents like cost, performance, location, and I will say more or less that's some of the, well, of course, if you need the resource for the run, the core, the edge, whatever, but they were basically the main characteristics declared. Nowadays, we were seeing the automation part and the security orchestration. So security is also one of the aspects that you may request when you need to, let's say, purchase or you need to rent or hire a resource for a short time. So why cannot include trust as another dimension that can be used as an add-on, not something that we may to omit other characteristics, but complement. So that's one of the views in which I think that trust model help us to operators and stakeholders. And also because we were talking about automation. And when we talk about marketplace, for example, we may introduce the concept of a smart contract. So we may declare the countermeasures or the action to take it into account if some misbehavior happen as part of the smart contract. So we are automating decisions together with or really similar to what others already did. So that's some 2 points that I will highlight.
So I think we are running out of time, but quickly, can you like say like, so how can like SSI and DID can be integrated with 16 networks? Like a quick, very like a plain answer, like SSI, DID in 16 networks, what would be the main things like to expect? What should be?
Okay, really quickly, benefits, for example, seamless, I will say, cross operation or cross operator authentication, because the chance to include decentralized identifiers remove the need of have central authority, like for example, public key infrastructure, that you need to rely in a central point if you want to be authorized or you want to, let's say, receive your credentials. With DID, we remove this bottleneck. Of course, we'll also include this technology in, let's say, the machine-to-machine communications that they will be part of the 6G. However, we have, of course, limitations. So if we are in an IoT environment, we may have resource constraint limitations, and those cryptographic operations that we have with the DIDs is one of the weaknesses. And if we finally have post-quantum, probably the DID need to evolve really quickly.
Thanks, Jose Maria. So thank you everyone for the questions and for the answers. So audience, it's your time to ask questions from the panelists, please.
Can you talk about the negative section or general? There is a indication, for example, those that are not into the fact to be a partner, are very interesting and of course,
It's for me the question. Yeah. So it's the way that we are testing our model can help on this. And also when we are working on a non-supervised setting, that means we don't have any labels for the attacks and the training data. So when we introduce new attacks on inference, on testing it, for example, then the proximity on the latent space, for example, in our case, spoke for itself, and it showed that there is a correlation of new attacks coming and that have not been introduced on the training, and it was working. Yeah, so it's basically mostly on testing it and how we train the model.
Maybe I can suggest my idea, what I have been thinking about that. I guess pre-processing of the data would be really important for this kind of questions. For example, improving the variety of training data would really helpful to fit your approaches, like perform well for different data sets.
Okay, so does that answer your question? Yeah. Right, great, thanks. So one question from the Q&A in the Zoom. So for Jonas, that is, so how well does the confidence metric generalize to AI models and learning techniques like reinforcement learning and federated learning and data domains like continuous and non-convex data scenarios?
Thank you for your question. To answer on data domains, we're testing it on continuous and also LLM agents, and it seems to be working so far. We have not tested it yet on federated learning scenarios. This is something that we would like to do, but also we have not tested it on reinforcement learning. We are testing it on continuous learning and mostly on continuous task learning. So introducing a new task each time, and it works, and also on AI agents, it works as well.
Okay, right, thank you. Thank you, Jonas. Any other questions from the audience, please? More questions? Arsenia, yes, please, yeah.
Given that they want to reduce neural monitoring data security, but not so good for performance. So where is this for?
For me, it's kind of really a trade-off, because yes, we monitor and if we monitor everything, that's really big inefficiency for us. But for the security, it's okay. But for privacy, it's not okay, and energy performance is as well. But here, there might be some techniques that we don't have to collect all the data for intrusion detection systems. For example, I'm just making up, we can use explainable AI techniques that can bring us just important features, and we can only evaluate the part of the data for the efficiency part. And while we are extracting explainability, this brings again some privacy concerns. And here we need to find a way to balance explainability and privacy by using some privacy techniques on explainability. So this can solve both security, privacy, and efficiency problem.
More questions from the audience, please?
Okay, if there are no more questions.
So, we'll do concluding remarks, so like.
Oh, yeah, of course.
Yeah, so maybe like 5 minutes, yeah?
Yeah.
So,
Slides?
I think there's like, that doesn't matter. Yeah, so, so just to like conclude everything like regarding the questions that I've asked, the answers that you have given, like, so, the questions that the audience asked, right? So, like, can you guys have like, maybe a 1 minute, concluding, remark on whether like, so 6G in AI, so what would be the main things to, like consider? So what would be the main driving forces? Like starting from here.
Well, with this, I would like also to partially reply to Betul. In 6G, the needs of automation is, let's say, it's very pervasive, okay? And AI, it's something that can help us. But although, let's say, the complete automation, zero-touch automation, it's the final aim, it will be a huge result, okay, for the research, and the research should keep pursuing this. Probably the human will remain a key factor in this process. So someone that say, this is right, this is not right, and take the responsibilities to make these critical decisions. Okay. Oh, yes, yes. We are far from there, probably. Yeah. The thing is that, just to conclude, maybe we can reach this complete automation, but it's not sure that we will use them.
Yeah, that's
Okay.
Yeah. So, can I go on the, like, what are the important things on AI?
Yeah, I think that we also need to focus on the general idea of trustworthiness. I mean, having robust, fairness, explainable, confident predictions. This is something that we have to start applying it in all the domains, especially in 6G, for example, because it's not only for the predictions now, it's also, we have to understand what we're doing and how we're doing it. Yeah.
I guess I'm going to highlight the same thing again. If we are mentioning trustworthy AI, we should consider all components at the same time. If we are looking for security, we should also consider privacy at the same time. If we are providing explainability, we cannot think without privacy. So trade-off should be considered for each components of trustworthy AI ML.
Well, maybe I am going to be a hater, but when I started to do my PhD about 6 years ago, my colleagues were laughing because I decided to work on 5G, and we had 4G at that moment. Now we go for 6G. Shall we go one step back and see what are the challenges that we compromised to have in 5G and we didn't do it, and now we are again put on the table to do in 6G?
Okay, so thank you everyone for this nice discussion that we had, and thank you for the audience for the questions and remarks. So I think I will conclude this session now, right? But thank you so much for like helping me to like do this.
Thanks, Pasika, and well done to all the panelists. So now we'll have 1 hour break. As I've mentioned previously, there is a poster session out there in the hall. So please use this opportunity to squeeze as much information as you can from the presenters. Everyone should be standing at their posters. There is also lunch provided. There will be coffee, tea, water. So please use that. After break, which is at 2 o'clock, we're coming back. There will be only 3 more technical talks and another panel, so it's not going to be as long as the morning session deliberately. So yeah, please do enjoy your lunch, and we'll see each other at 2 o'clock in the same location. Thank you.
No.
Thank you.
We adjust the camera. Yeah. We need to catch everybody from. Can you go to a lunchroom and just ask everybody to come in? Tomorrow, we're not getting nice like it used to be. We will take them with us into the lunch. So maybe the idea with the table on the tomorrow. Let me see if they are uploaded. Oh, you send it to me? Maybe I send it to this bit. When did you send to me the newer version? Oh, then it's not. But that's no problem. We'll replace it. That's fine. I will replace it in a moment because I need to access my email and then send it to Vidura, and this has to go here. Sorry. No problem. No problem. I'll do it. Okay. We will resume now. We're just a couple of minutes late, enjoying lunch. Is it sharing? No. Right. So I hope everyone can hear me, and also online people are back. The next presenter is Stefano Tomasin from University of Padova, also a partner in Robust 6G project, and the presentation is on physical layer authentication for 6G network. It's the first presentation out of the 3 technical presentations this afternoon. I just want to remind you that we will also have a second panel led by Michel Rossi with the 3 presenters, and then we'll wrap up with coffee. Hello, Tommy. So off to Stefano. The stage is yours. You can use the arrows or you can use the mouse.
Thank you. Thanks, Bart, for the introduction. And so welcome to this afternoon. There will be talks related to physical layer security, which is one of the main components of the Robust 6G project. I'm talking about authentication. And the first thing that I would like to highlight is to give some idea of why physical layer authentication is welcome or needed in 6G network. So it's a solution that may complement the cryptography-based authentication, which is already there, and strengthen the security. We can see, I mean, in this complementary vision, let's say, can be seen as a 2-factor authentication. So where the physical layer authentication is playing the role of one of the 2 factors, that is basically enhancing security like there. It's a lightweight mechanism in general because it's based on signals that are already available in 6G network, like physical layer signals, and knowledge of the channel, which is essential for the communication purposes anyway. And so it's also suited for devices with limited capabilities, resources. And we all know that 6G is going to extend even further, even more than what 5G already did, the application of communication the inclusion, sorry, into the communication network of devices with heterogeneous characteristics, so including those that have limited capabilities. On top of this, or as a further substantiation of the usefulness of physical layer authentication, we have to remark that in November 2023, there was a document issued by ITU to describe what is going to be the IMT 2030, so the 6G in the ideas of ITU. And in this document, which is not so long, it doesn't mention so many techniques, also physical layer security technologies are included. It's not like a casual mention because, again, if you check the document, you will see that so many other technologies, even those that were mainstream for 5G and actually didn't come with 5G, are not included there. So I think it's a mention worth to be taken into account by 3GPP. So on this expectation, let's say a few more words about what is authentication, what is the physical layer authentication, in particular channel-based authentication. So the idea here is that we use the channel characteristics that are connecting, that are related to the specific position of two devices as an authentication feature, so as a fingerprint of the communication. So we can imagine two phases. One phase is the user association, in which there is a first recording of the fingerprint, so of the channel features that will characterize the link between two devices. And this is done once, or let's say every time the channel changes. And then there is a user verification, which is done whenever a message is received. And in this case, what we do is to check if the channel that was observed in the first phase is actually reappearing in when other messages are received. So if in the other messages that we are receiving, we find the same characteristics, the same features that we find in original fingerprint acquisition, let's say. So there are two kind of errors in this procedure, false alarm and misdetection. So the receiver may be wrong in two ways, either accepting as authentic something which is not authentic, or rejecting as non-authentic something, a message that is actually authentic. And we have to find a trade-off in this between these two errors. What the attacker can do, many things. Well, the simpler attack is a situation in which the attacker, here called Eve, is transmitting from another location. So she will expose, she will be characterized by a different channel, by a different fingerprint. And she may be lucky or not, depending on how much the channel over which her signal is going through is similar to the one of the channel connecting Alice to Bob. Can be also more elaborate attacks in which Eve pre-codes the transmitted signal, so that she's trying to, understand which is the channel characterizing the Alice-Bob link. Eve can have some side information, so can get some information about the channel condition from, for example, her observation of the channels to Alice and to Bob. And she can try to infer which is going to be the channel between Alice and Bob, thanks or related to this side information. And what also Eve can do is to perform multiple attacks, so to repeat, to perform several kind of pre-coding and attempting to guess which is the correct channel condition between Alice and Bob by changing every time the signal that she is transmitting. So here you have a picture where we see what is a good strategy for Eve to attack. She can divide the space representing the channel features, in this case a two-dimensional space, into squares, and try to recreate the signal that are associated to the center of each square. So she's going to cover the whole space with suitable, with a suitable order there. And the circle that you see here is how Bob is making a decision. So whenever Bob receives something that is falling without the specific circle centered around the channel that Bob is expecting when talking with Alice, then Bob will accept the message as authentic. So as you can see, by carefully choosing the size of the squares, let's say, with respect to the size of the circle, and carefully choosing the order by which Eve is selecting the point, she can actually performing multiple attacks sooner or later getting there. Of course, this is also common to cryptographic authentication, because this is a kind of an exhaustive attack. It's like trying all the possible keys in a secret key based authentication. And also in that case, sooner or later, of course, the system is broken. So this is kind of the equivalent. So the number of points that Eve has to explore basically indicates the level of security of this authentication system. And also there are situations that have been studied, and also Ersi and Laura has been studying these cases recently, where the attacker is actually not allowed to do to explore all the points because of physical limitation of the position of the attacker, of the number of antennas, and with the specific features that are used by the defender. So this is just a general picture. Then in some specific cases there can be further defenses that can be deployed. So one way to further strengthen the physical layer authentication is to include a challenge response mechanism where basically we kind of mimic what was already there in the cryptography. There is a question that is asked to which only the legitimate transmitter is able to provide the correct answer. And in our context, the question and the answer are physical layer signal. So what we exploit here is the possibility of using partially controllable channels. So the possibility to modify the behavior of the channel. So the expected fingerprint that we are going to observe at the receiver according to some random strategy that corresponds to the random choice of a specific question to which we expect a specific answer. So in practice, what happens can be applied in several contexts in a 6G network. So here are 3 examples where we have a partially controllable channel in 6G network. One is the case in which we have an intelligent reflective surface that clearly modify the way signal propagates over air. So is a way by which we control the channel between the transmitter and the receiver. Presence of a relay, the possibility of using moving devices like drones that by changing their position will modify the channel that they expect to see from a specific transmitter and the receiver. So whenever the receiver can modify, and even the transmitter, we are studying also that condition, can modify the propagation channel in some random, unpredictable way to the receiver, then you can apply the concept of challenge response authentication. So the challenge response authentication protocols reads like this. We have the first phase in which the receiver has to understand which is going to be the list of answers that are expected to be obtained for each specific question, which corresponds here to the fact that we explore the channel conditions. So the receiver will estimate the channel under different configuration of the channel. For example, think about different configuration of the RIS. And so here is this is the phase in which we build the codebook of questions and answer. And then we use this codebook. So the receiver will set a random configuration of the channel, for example, a random configuration of a reflective intelligence surface. This corresponds to choosing randomly a question. And it will cross-check that the signal that it receives shows the channel features that are expected, that were recorded in the codebook in the first step, so that the receiver can say that he's receiving the right answer to the random question that he was posing. Eve is supposed to be in another position with respect to Alice, and therefore she will give to Bob a different answer, so she will have a different channel to Bob. There are, so in the specific case of intelligent reflective surface, you also have to consider the trade-off between the communication and security, in the sense that there is an optimal configuration of the RIS for communication purposes. And here what we have explored, for example, is random variation of the configuration, in particular of the phase that you have in each element, where the randomness is a uniform variation around the optimal phase that you can select at each element in order to maximize the capacity, with a specific interval, angular interval there. So we are perturbing the behavior of the RIS a bit with respect to what is going to be the capacity optimal performance, but not too much to obtain a trade-off between security and performance. And here you have an example of performance where you see that the probability of misdetection, which is the probability of success of the attack, is quickly going to 1 if you do not apply the challenge response mechanism. And this is because by exploring the space at the end, it is able to break the authentication system. While if you introduce challenge response, because of the fact that every time you have a different channel that a different random question, let's say, that is posed, and correspondingly a different response that is expected, as you can see, even if the number of attack grows, the probability of missed attacks doesn't go to 1, but it has a floor, depending, of course, on what we set in terms of probability of false alarm. There is a trade-off there between false alarm and missed detection. We also investigated more sophisticated attack strategies, referring to the Kullback, so working with the Kullback library divergence that give us bounds on the achievable error regions, on the trade-off between the false alarm and misdetection probabilities. We also studied defenses against that, and what you can see is that even with these more sophisticated attacks that are refinement and kind of optimized to better address the fact that we are using a challenge response authentication procedure, still we are able to provide good performance in terms of trade-off between false alarms and misdetection, of course, depending on the knowledge that Eve has of the environment. Here is an example of security communication trade-off, where we see that if you want a lower misdetection probability, so a more secure system, the capacity actually decreases. The reason for this is that the way we achieve security is introducing randomness in the channel, randomness with respect to what is the optimal configuration of the RIS for the capacity achieving solution. So what would be the optimal configuration of the RIS to maximize the capacity. So if whenever you deviate from this configuration, the capacity, the achievable rate will decrease, but this will also benefit the security. So here is an example of investigation of the trade-off. Of course, whichever number you see here, you have to take into account that typically these results are reported for a limited number of antenna and a limited number of elements of the RIS. If you want to have a lower success probability for the attacker, you can increase the number of antennas, and you will have a scaling law there to decrease the success of the attack. So these are, to show basic trade-off that you have there. This is another example that we investigated more recently about the use of movement of drones to perform attack and defenses, again, with this idea of challenge response. In this case, we had both the attacker and the defender that are flying in space, so they can both change their position. And so whenever the attacker is changing the position, is inducing a different channel to the defender. So now we start a kind of a dance between the attacker and the defender. And in this way, so we have two strategies: the strategy of the attacker that will randomly select the position, and the strategy of the defender, which will again randomly select its own position. And we analyze this scenario with the game theoretic approach, identifying Nash equilibria, so identifying which is the best strategy in terms of Nash equilibria that the two actors, the two competing agents should actually do. Also including the fact that there is a kind of an energy constraint, at least for the defender, that you cannot spend too much energy just to dance in the air for the purpose of security. So we also took energy into account in this example. That's it. So I try to give you some hints about the fact that physical layer authentication is useful in 6G system. Think about the possibility of implementing a two-factor authentication. I also delve into some results and some research that we are doing that is using this concept of challenge response authentication that can be applied in several contexts, is yet to be explored. We explored some of the attacks, some of the defenses. We explored some of the strategies that attacker and defender can take there. But of course, there are many things that we should investigate. But definitely, this is making the system more robust against possible future attacks. That's it. Thank you.
Also, we'll keep the questions until the panel, as you will be part of it. So now we are moving on to the next presenter. As usual, the right arrow or the click. Some timing there and work out the extra.
Okay, thank you. So good afternoon, everybody. As you can see, I'm the second speaker to use overleaf after my colleague, so we are the nerds here. So today I'm going to talk about robust physical layer authentication and key agreement. And I'm going to give a couple of thoughts on how this can be useful in 6G. Acknowledgements first. So the results I will present today, they have been financed partially by 3 main projects, and of course, robust 6G. And I will not make any assumptions that you have a background or even an interest in physical layer security. So I will try to motivate you a little bit and give you a background on some basic concepts. So why do we need new tools, and what are the fundamental background that we need to understand those new tools? And then I will move on to discussing some potential applications. So 6G security, why do we need new tools? Pretty much for the same reasons that we did for 5G. And of course, there are new attack vectors, including machine learning, but I'm only concentrating here on the open issues that we already had in 5G. So the first one has to do with latency. So with the introduction of ultra-reliable, ultra-low latency communication systems, in other words, autonomous agents that need to communicate probably with each other or with a roadside-based unit if it's a smart vehicle in real time, in sub-milliseconds sometimes delay. This becomes an issue when we have to apply authentication protocols that come from the realm of cryptography. And this is still true today, even after the introduction of new enhanced techniques for post-quantum handshakes based on post-quantum lattice-based, for example, signatures and so on. There is a second issue that has to do with the scalability, of course. In other words, when we deploy a massive number of very simple devices, some of them as simple as RFID devices, is it possible to envision that each one of them will be identified using the standard techniques? So just as a reminder, in 4.5G devices that have a SIM card, they use a quite elaborate protocol that basically is based on deriving passwords from the SIM card and used for authentication. We also have the ability to use public key infrastructure, but that basically comes with the cost of digital certificates that are costly, and we cannot envision that every simple IoT device will be equipped
with either a SIM card, so there will be a lot of seamless devices in the future, and actually there are at the moment, and they will be so cheap that we cannot really believe that each one of them will be identified with a digital certificate. This is out of question. So what happens in that case? And of course, everything we build from now on needs to have the guarantees of post-quantum resistance. So there are, of course, definitely the first post-quantum cryptographic suites that are available since 2-3 years now, maybe more. The question is, are they simple enough for those simple devices? And what do we need when it comes to software updates in the future if those devices are deployed for 10, 20 years? Because right now we are used into a paradigm where the devices are deployed for 3 years, then you throw it away, you don't have any hardware software incompatibility. Is this going to be true when we deploy very simple devices for 20 years in the future? So these are, I think, the open questions that actually make us rethink whether some techniques, probably from the realm of physical layer security, could be helpful. And when I'm saying helpful, I do not mean for authenticating mobile phones in the network, but for some other applications based on the constraints that I've shown before. So in this talk today, because I only have 22 minutes, because I also asked for 2 minutes extra from Bart and he gave it to me, I will only focus on 2 possible technologies. So localization as an authentication factor and secret key generation from shared randomness. And I will share some thoughts on how we can use them in the future. So just a quick overview of fundamental ideas here. So when we look at the wireless channel, it is a composite physical process. There are lots of things happening. There is path loss, there is shadowing, there is small scale fading, and so on, scattering. So the physics behind it is basically the physics of electromagnetic waves, and based on the environment, we might have a more noisy communication link or a less noisy communication link. When the circumstances are good, so we have a good quality link and line of sight, then as you might know, we have good chances of high precision localization, especially looking at high bandwidth systems that come with sub-terahertz and millimeter waves. So on one hand, we can do probably high precision localization, but there is a trade-off, if this is the case, with how much entropy there is in the environment, because this is the second pillar, this is the second source that we can use to achieve security goals. So if we have a high entropy environment, then we can envision that this entropy can actually be distilled and we can generate secret keys at 2 remote locations using a very old protocol since the 90s. It's pretty much a reflection of what they use in post-quantum, in quantum key distribution. There is a parallelism between the two. So we can exploit this source of shared randomness between 2 remote wireless devices to distill keys. And as you can understand, there is a trade-off between those 2 operations. When I can do one very well, probably I don't have enough to do the other so well. To give a visual, because it helps to look at figures. So if we look at ray tracing, then basically we have a snapshot of how the electromagnetic waves are propagated in a given environment, right? And this is a static snapshot. And we can use this type of snapshots for authentication, because this is what is going to help us for location-based, for localizing a device and using the location of the device for authentication. On the other hand, if we look at small-scale fading that is represented here, we can see that the variations of the channel state information between the devices, first of all, it's highly reciprocal within what we call the coherence time of the network, of the system, sorry. But on the other hand, it is unpredictable. And it is this unpredictability that is basically the source of randomness for generating good keys. So on one hand, we can see that we have large-scale fading effects that can be the source of good authentication. These are largely predictable, but that's not a problem for authentication. What we should be able to guarantee, however, is that these, let's say, location fingerprints are highly separable. So I can have good accuracy in my localization. I can identify with high precision the users. On the other hand, we have small-scale fading, which is basically these rapid variations due to the scattering effects of the environment. This is a good source of entropy. What I need there, if I'm going to produce good keys, is what we call unpredictability, and I will explain in just a moment. So the requirements for authentication, on one hand, is the separability that I already touched on, and then, of course, the unforgeability. So we should not be able to impersonate, to spoof, if you want, a legitimate device. So these are the two requirements for authentication. When it comes for secret key generation, if we follow the path led by our cryptographic community colleagues, then we need unpredictability. In other words, to put it simply, having seen a long enough sequence output from the secret key generation, I should not be able to predict even a single bit of what is going to come in the future as an output. In other words, the achievable secret key rate, when we have two legitimate users, A and B, Alice and Bob, with observations ZA and ZB, is upper bounded to this conditional mutual information expression. And this conditioning is based on the observation of a potential adversary ZE, right? So I might have an adversarial node that is observing the channel. If we look at the full protocol that has been around, as I said, since '92, basically, and almost simultaneously proposed by Maurer and Caesar and Kerner, this has been encapsulated, this unpredictability requirement has been encapsulated in this last part of the protocol, which is known as privacy amplification, and is based on the estimation of the conditional mean entropy, upper bounding basically the key length that we can extrapolate from the environment. So if the environment is static, you can understand that my chances for extracting good keys are low. This rate is going to be lower. If the eavesdropper is on my shoulder at the wavelength away, then this key rate is also going to be smaller. Okay, and just to mention here, this conditional mean entropy, it gives a worst case, let's say, performance analysis, as opposed to the usual entropies that we use and are an average basically metrics. So we follow here what they do in cryptography and they take into consideration a worst case scenario. All right, so this is the background. This is what we wanted to achieve. So how can we construct robust physical layer authentication? During the lifetime of robust 6G, we were able actually to showcase something that initially started as an intuition, as a hunch, if you want, and formalize it as a theorem. And we believe that this is actually an important contribution because for the first time, we were able to demonstrate that there exists a physical feature, which is the angle of arrival in a digital array MIMO system that cannot be forged. So an adversary cannot impersonate the angle of arrival of a legitimate transmitter as long as their angles are not identical. This is irrespective of the number of antennas at the attacker, as you can see in this figure. So the attacker might be more powerful than the legitimate device, which here has just a single antenna and is being authenticated by Bob here that has a digital array MIMO. This, however, is not true when I change the technology of my RF tuner and I move to an analog array MIMO authenticator. And this was actually a very surprising result because for the first time, we can see how hardware complexity, I mean, not only impacts the performance, but also the security guarantees of a physical layer security system. And we were quite surprised by this result. So this is the first ever, to our best knowledge, physical layer authentication approach that can be proven to be robust against spoofing attacks. In other words, is unforgeable. And this can be demonstrated here by the mean square error, which in the legitimate case falls with the SNR and reaches a plateau at very, very high SNRs, above 20 dBs. In the case of a forger, does not actually fall at all after a certain point, reaches a plateau. Right, so the unforgeability, which was my first requirement for authentication, at least in certain cases, we can tick the box. So if it is the base station doing the authentication, we're good. So what are the separability properties? How accurately can I authenticate users in a real scenario? So to test this, we proposed a multi-stage hierarchical classifier to perform angle of arrival based authentication. So we have the channel state information data that are converted using very well-known angle of arrival estimation algorithms such as Musing and Esprit. They are converted into angles of arrival. And then we used a different type of classifiers, a large number of them for comparison reasons. We had a hierarchical classification system where first we were identifying whether the specimen, the CSI, the input CSI was actually coming from a line of sight or a non-line of sight region. I will show what this means in a few seconds. And then we had a second stage classifier based on the decision made by the first binary classification. So we applied this approach to an outdoor data set that was provided to us by Nokia. Nokia is not consultant, is, what is the word? Not a partner. Yeah, I mean, is a observer of our project. So they were kind enough to give us a data set on which we could work. It is from their campus in Stuttgart. It is therefore an outdoor environment, which is highly difficult when it comes to RF positioning and localization. We were working on FR1, which is at 2.18 gigahertz. We had 64 antennas on a 4x16 arrangement, 50 FDM subcarriers, and there were a number of trajectories here that were termed tracks. So in this map, we had the blue tracks that are line of sight and the red ones that are non-line of sight. Out of all of the possible tracks, which were more than 26, we selected 10 of them just to showcase the results. We have 5 line of sight tracks and 5 non-line of sight of tracks. And we applied this approach here of a hierarchical classification. And we achieved an accuracy that exceeded 96% in identifying the track based on the angle of arrival. So our first stage classifier between the blue and the red trajectories had 100% accuracy. The second stage classifier was shown to perform with an accuracy that exceeded 96%. And yesterday, my student said that for the line of sight, he even reached 100% by changing, fine-tuning a support vector machine, which showcases that, yes, we can achieve very high separability. So there is a good use case about this. But should we really care? So, okay, you have put a lot of effort, you made it work, so what? This actually comes back to the beginning of my talk, which is about the competitiveness of these type of techniques for application in 6G because they are lightweight compared to classical cryptography, to post-quantum cryptography. And here we performed a one-to-one comparison based on the number of CPU cycles with dilithium 5, which is used for signing and verifying signatures. And this is just one part of the authentication protocol, just to clarify. And with our method that includes the AOA estimation. So the angle of arrival estimation, let me remind you, is useful for beamforming and can be done, even should be done in certain cases, even without outside the security protocol. And our own two-stage classification, which was not even optimized to give good complexity results. Okay, so what I'm showcasing here is that we win, even if this was not intentionally our goal in the beginning. So the sky's the limit. If we put if we optimize those procedures, they can work even in an outdoor environment. And another point that is very interesting here to be made is that we can look at the fusion of the communication setup link and the authentication procedure, because to apply cryptography, you need to have the communication link, the wireless communication link running. Otherwise, how are you going to apply cryptography? And here we have the chance to fuse the two stages because AOA estimation can, it is also one of the apparatus when we do beamforming. Therefore, when we are really setting up the communication link. So I think it is worth exploring much further, but I believe this is really worth anyone's attention. When it comes to robust secret key generation, so in the past, this was like my niche area. I have worked on that for more than 10 years. And I have specifically worked on how we can combat against all sorts of attacks. So from eavesdropping to man-in-the-middle and spoofing attacks, to denial of service attacks, tampering attacks, and so on. So for all of those, there are solutions. And if you're interested, I have put a comprehensive list in this book chapter here, so please feel free. The last thing that was missing there from more our point of view was the speed, was the complexity. To run the conditional mean entropy estimator, which is a very heavy statistical test, unfortunately, this cannot be done in real time. So essentially, we needed from minutes to hours, and in some cases in static environments, even days to run the conditional mean entropy estimator, and this was a bottleneck. So we were not delivering what we were proposing, which was fast and low complexity secret key generation. And this last, let's say, hurdle, we decided to overcome with the help of supervised learning. So we ran offline this heavy statistical test in a given environment, and then we trained an LSTM network basically reproduce the results under the condition that we should never underestimate the required hashing rate. And it worked. We were able to demonstrate it last week in the 6G Summit with a live demonstrator that included context awareness. So the information about the environment, the existence of line of sight or non-line of sight and so on was available. This was a physical context. And we were able to showcase how good quality, high entropy secret keys could be actually generated in real time. Right, I only have 0 minutes. Time is up. I just wanted to make, to steal another 30 seconds here and say that from our point of view and what we are really working on at the moment is how to incorporate physical awareness into a larger concept of trustworthiness that incorporates the physicality of the 6G radio access network. And to give you a simple example of where I'm going, if the autonomous agent is not at the right position, there's no need to make any other, let's say, intrusion detection or any other very elaborate technique to identify that an attack has taken place. Okay, so I will stop here. Thank you very much.
The questions can be asked during the panel. So now we have our last presenter, Tommy. Hi. So we are staying in the physical security layer domain, as you can tell. I just want to also remind when Arsenia mentioned the demos, we also do have quite a few nice demonstration videos in Robust 6G website. So that covers a slightly different work, the challenge mechanism that you have provided us with. But we do have a lot of demos, also one from Stefano. And yeah, Tommy, the stage is yours here. Are you, let me just, did we upload the slides? Okay, have it. Afterwards. Yeah, here, I have it. Okay. Oh, it's this or,
okay. So good afternoon and thank you for inviting me. So the title of my talk is The Potential Physical Layer Security in 6G. As you might know, I'm a more physical layer communication guy than a security guy, but we try to learn because we think this is a very important topic. So that's my starting point. So I will do a little bit quick recap on where we were 4G towards 6G and something about threat modeling. Then I will talk about some work we have been doing and are doing on physical layer security related to jamming mitigation, glimpse on what we are hands-on work on now for eavesdropping mitigation and secret key generation, and then some take-home messages. Let's see if I stick to my 20 minutes. When did I start? I need to keep track. Okay. So at Chalmers and my team, we've been very active in mobile system generation from 4G onwards to in this big EU projects, particular to design system concepts. A couple of projects there. So at the moment, HexX2 is still ongoing. Robust 6G, as you might know, many of you, and SECURENET, which is a project converging also the transport networking with both fiber optical and free space optical with wireless. And there we see a lot of opportunities too. So as a quick recap on what 4G in a one line was about, it was to get the mobile internet with the rich multimedia to the pocket, IP-based. And that's what we did. And I think it works quite well. 5G, one step was to do that, put that on steroids, getting high capacity, so enable densification, and very also high data rate per link towards a more high speed, high capacity mobile internet. We did that by addressing new spectrum, which are partly taken off in a limited way, but sooner or later maybe. Another track was to enable massive uptake of Internet of Things applications, because started with cabling a long time ago, then a lot of different wireless technologies, but to really make this as a scale and cost efficiency of operations, the mobile industry and me think that the mobile industry has a role there. So that is what we worked a lot on there to enable that scalability and efficiency and so on. And that continues 6G also towards zero power devices and so on. The other track was what I've been calling, some others also, Internet of Skills, to enable remote interaction on distance. So not only an internet of information, but an internet of remote actions. So for example, to drive, helping a level 4 automated car, where it can do everything except when it gets a problem, it stops at the side and say, hey, I need help. Yeah, and all the way to remote surgery. 6th generation, there were a lot of use cases in 5G because 5G was not only about mobile internet to private consumers or business consumers, it was also to enabling a new way of earning money in the mobile industry. So addressing different kind of vertical industries, and there have been a lot of structured work on that for industrialization, automation, in production for more or less autonomous vehicles, smart cities, smart grids, and so on. So, and then we have seen a further trend on deep digitalization of the society. And there we think 6G is really having an important role. We are converging. It's not only about an Internet of Information, good to have things. No, their dependability. We rely on it. We want and we need to interact in the physical world with the digital world and then the human values in a very tight way. So we go towards some seamless digital virtual world experience. And here is where trustworthiness is one of the key pillars. Because we also have a lot of challenges, and they are summarized in the United Nations Sustainability Goals. There were 17 on them. We analyzed them carefully in the HEX-2 project, and we saw that there were 6, 7 where we really could make a change. All of them we could impact and help. So, and once again, these are not business to business even. Here we are using public money. Here we're using public trust. So if the mobile industry wants to play a role here and help out, we need to be reliable, trustworthy. We say we can do it, and we need to be able to do it and deliver. Yeah, and then from a tech point of view, we have converged communication, sensing, computing, and storage with AI towards some kind of internet of also senses. So human feeling world or remote interaction. And there we are also collecting a lot of sensitive data. So privacy, we do online sensing. We plan to do that as an integrated part of the network. This information will be very important, very sensitive. We need to do that in a trustworthy way. So many people are working on techniques like federated learning or distributed federated learning, where we try to learn things that we need for this seamless interaction with the physical and digital world, but to do it in a low-risk way. And also, I think they go hand in hand with also low complexity and then efficient solutions. So some of those use cases in 6G were in the area of sustainable development, massive twinning, immersive telepresence, robots to collaborative robots, and local trust zones. And you see many of those, it's so important we get trustworthiness. So one of the projects, I wasn't sure about the audience here. I think a lot of people know here have roots in Robot 6G and are fully aware of Robot 6G. I just wanted to acknowledge it. There were also, I think, quite many in the online community. So we have a EU project meeting in Robot 6G coming 2 days. And that is one of the projects taking over in the second wave of HEX-2 first flagship initial architecture works to spin off what are really needed, and Robot 6G making a holistic view on what a security framework could look like. And there we have physical layer security part of it. So at Chalmers, we are trying to glue together the computer science department is quite strong on security. On my side, wireless communications, and also my colleague there on sensing, and Weimers are working on physical layer security aspects, and we try to glue this together. And the security department hired, computer science department hired an assistant professor, Masoom Rabbani. I don't know, Masoom maybe is online even listening now. Unfortunately, he couldn't come in person for this meeting next week, but he will be very active in Robot 6G from now on. We are developing now, yeah, I'll come back to what we work on. So there are a lot of opportunities and risks in a wireless network with dense interactions. So we have jamming, spoofing, eavesdropping risks, and there are a lot of different channels, and we can control them. I don't spend more time because Stefano already talked about it. So I have a strong focus on densification and scalability of wireless infrastructure. We worked a lot in beyond 40 times on different kind of cooperative base stations. We worked on convergence access backhaul. In 60 times, we work on further densification with a lot of access points. that are dynamically interacting, and you try to keep the user and the user needs in the center. And here we also open up interfaces then. It's not so there's an initiative of ORAN, Open RAN standardization. We open up there are different suppliers, and there are new attack surfaces that are creating risk and opportunities. And then Stefano talked about risk, which I think is a good opportunity too. We talk a little bit about it too, but I spend less time on that. So DMIMO deployment can look like this. We have a lot of small access points that are complementing the macro base stations. We mount them on house walls, we mount them on traffic lights, and so on. So as you see, there will be many, there will be small, there should be less costly in hardware, there should be less costly to deploy. People might come and smash them, people might come and try to eavesdrop them or put up fake access points and so on. So this is the new infrastructure we might be living with. And it's not only the big macro base stations or base stations up on a house roof or on a tower where that's hard to get access to. And then there are behind those access points towards the, sometimes they are interacting with the macro base stations, sometimes they are going directly to the transport network. And they will have different kind of media that can be wired, that can be wireless. The wide media can be optical or it can be electrical, like Ethernet. And then there are a lot of different transmission approaches here, including analog and so on. In general, we have seen here that this densification is very important for especially addressing the higher care frequencies, which are getting important for 6G. If we want to do the fancy use case we have in mind, we need to get access to what we call the centimeter wave bands, 6 gigahertz to 15 gigahertz or so. Some call it FR3 as a working band. It's not defined. But there we really need these kind of technologies. So I have one a little bit semi-messy slide here. I will not go in fully in detail, but I will show we did some initial work on the security analysis for DMIMO as part of the HEXX project. Some of the things we observed was that if we do multi-connectivity of users being connected to many access points, we need to have some kind of arrangement for the authentication and key agreement between the network and the user to multiple radio units. If we do this, and this means then that there's some extra overhead here. If we do joint transmission, then the user would not, in the downlink, the user would not see that I get the signal from many access points. The data happening over there. But that would mean that we need to do this together, a common encryption key between all the access points, because as a user, you think it's one channel. For the control plane, we see here that we also need to secure the MAC layer. We might also need to support multiple security associations of the users. And once again, there will be cheap access points, so we maybe should need to do things more centrally here, because we cannot fully trust those distributed access points. This is not a motivation for them. That should be closer to the user. Then we can really do good things at high frequencies, because we get line of sight, less blocking, less attenuations of the signals. But we get closer to the users, where that's an illustration I showed before, the risk of smashing them or manipulating in different ways. But that should really be easy and easy to deploy. This means that there will be less trustworthy than traditional base stations. In the Robust 6G project, we had one initial overview on threats in 6G as foreseen, building on 5G threats. RC was one of the key contributors here with your legacy work in this field. I just do a commercial of it, that report. When it comes to DMIMO, we track the structures from the STRIDE methodology perspective, and we identified some of the attack surfaces and some threat definitions. There were similar works done on RS, on federated learning, on some other technologies in the report. I leave to there. I think we will share the slides after also. So with that, I want to spend some time. I think I have like 7 minutes maybe to go, 6. Some work we've been doing on physical layer technologies. One is on assisting, I don't see the title myself due to the Zoom. Risk-assisted interference or jamming mitigation for uplink non-orthogonal multiple access. So here we have this kind of RDSs deployed, and then we have a set of users. In particular, here the users are doing uplink communications, and they are doing it in the same time frequency spatial resource. So they're overloading the signals in amplitude. And then the task at the receiver is to resolve those signals. So we need to maintain a certain power level difference at the receiver side, or more in particular, signal to interference and noise ratio, because then we can do what we call successive interference cancellation of the signals. We can detect the strong signal first, and then we subtract it from the received signal, and then get rid of that energy, and then we can also detect the weaker signal. So that is in general the task. And then a jammer might like to destroy that. So we are looking into a jammer with a lot of antennas. It can do strong beam forming and try to drown the base station and destroy this signal to interference and noise ratio that we want to maintain at a certain level. So we looked into what can we do with a reconfigured intelligent surface being deployed here. So the jammer tries to maximize here then, and then the RES tries to mitigate that signal by listening, also using some of the energy coming from it, and then amplify by beamforming gain here towards the base station, and then do this more or less out of phase. So if there would be no users, and ideally the RES should be is to send the signal being received here, the signal copy coming from here should be minus that signal. Then the sum will be cancelled, and there will be 0 interference or jamming energy. The whole signal will be 0 out. But the RES cannot do it selectively. It can just manipulate the electromagnetic wave, so it will optimize its amplification and phases on all these surfaces or the tiles, and then jointly optimize what the configuration be. Because our goal we are set is to have fulfill a target on the performance of the users in uplink. In particular, I call this sustainable design. We are not maximizing the throughput for the users. We are designing what is the required service they want and they pay for. And then we don't overdo it. So the target is to have a certain SINR, a signal to interference and noise ratio for the 2 users at the base station. So we can decode them and fulfill the targeted data rates and reliabilities. Not overdo, not less. And then we are minimizing the total power they need to send by maximizing or by optimizing the configuration on RES. So we partly mitigate the jamming, and we partly amplify those signals accordingly to the needs, so that we reach the service targets. There are some more questions in the papers here that if you're curious, you can go into. Actually, I could highlight that there are 2 works. The initial work is a conference paper available. The journal paper is available in archive, and it's under revision. So these results I show here is from the article version, and in the article version we have been working quite hard on. It's also that have been working on this, to enable optimization of a large RES. And that's the key, because reconfiguring intelligent surface in its basic form doesn't amplify the signal. Then we need to be large to get the good beamforming gains and array gains. So here we've been able to optimize up to 130 elements. And as you can see here, we see the sum user power needed to meet the service targets as a function on the number of RES elements, and as a function, and the different curves are for the number of jamming antennas. So 4, 8, and 16. As you can see then, with a lot of jamming antennas, we need more power, whereas and we can mitigate with a larger RES. What is interesting also that we allow absorption at RES. So, and that is very useful where we have not so many RES elements or them proportionally as many antennas on the jammer. Then it's very good to attenuate the signal. We absorb energy at the RES. Whereas we have a much more degrees of freedom at the RES, we can work in the spatial domain, and then we don't need to absorb the signal. So next work we've been working on here, one slide. This is ongoing work. We are working on eavesdropping mitigation, and there we do it in the sense of integrated sensing and communication, where we are sensing where the target is. We help the users to get that information, optimize their beamformer, so we maximize the signal here and minimizing at eve. So we come back on that. We have come quite far now, but we will talk later on. Another area we work on is integrated, as I will wrap up, an integrated sensing communication, where we are working on DMIMO with very flexible sensing and communications and optimized beamforming, optimized resource allocation for sense communication. And the final I have is on secret key generation, and that is motivated by that we are working on acknowledge that the communications are getting more geometric in 6G. We are densifying with higher frequencies. We can start to record the signals, to learn the signals online by sensing, sharing information, modeling offline, and confusing with dynamic online information. So we are working with this, we call it digital twinning, radio digital twinning, where we are optimizing how we represent the radio information. And then we're looking into how we best can use this for secret key generation. And there we want to collaborate with RC knowing how to do them. But me and Masoom are now working on different techniques there. So we don't have any results yet, but stay tuned. So sorry for taking a minute or two too long here. The take-home messages are 60 aims to the societal needs. We should need to remember that the security community is crucial. Trustworthiness is in the heart. Multi-layer cross-disciplinary security solution seems to be both a need and a promising approach. And physical security based on integrated sensing communication has the potential to contribute to 60 trustworthiness, both with knowledge from and mitigating actions in the physical. So with that, thanks for listening, and the questions is to the panel now.
So we do now have the panel. For that, we also have slides on the pen drive. Okay. Yes. Yes. Okay, so the panel here is moderated by Michel Rossi. Of course, yeah. Yeah. Oh, Mike. So I'll be doing swapping between the video and the presentation. Test. whoever speaks first.
Okay, so I understand you guys are a little tired, a day full of information and contributors. So bear with me for this last session. So I am Michele over here, and then we have three excellent professors here for the panel. Professor Tomasin, Professor Corti, and Professor Tommy Svensson. So they are all experts, as you have seen now in their presentation, on security systems, wireless communication, mobile cellular systems. So they are really great and very famous researchers around Europe. So it's a privilege to have them all here with us to discuss about these things. So I have prepared a few questions and few slides just to let's say, simulate some interaction with them and to hear what they have to say. I mean, most of this that I'm going to ask was already covered somehow in the presentation from before. Now we try to maybe to draw some conclusions and to understand what is the status of security for 6G system especially. One thing that we may understand also from the previous presentation, it was said by all of them, I believe. 6G systems are very complex. They are probably becoming more complex than 5G. So there is an extensive use of artificial intelligence in those systems. So there's going to be a distributed artificial intelligence-based training algorithms for network optimization for anything you need. And also there is a number of low-end, low-cost IoT sensor nodes that are going to be added to the network, maybe also mobile cars, maybe drones, maybe, robots. So we have new network elements that are going to be included, and also new data sharing that is happening everywhere for the training of AI algorithms and for dealing with these new data generators. So all that is making these networks more prone to attacks. So this is not good news for a security point of view, I believe. Also, the IoT nodes that we are attaching, connecting to these networks are low complexity. So they are dealing with simple communication protocols or security-based protocols. So we need new attack surfaces are emerging because of this low complexity of the endpoints. So the first set of questions will be around this main, let's say, challenge. Are standard security means, like we are thinking about authentication means, encryption means, still enough for this type of networks? Or maybe there are alternative approaches that should be tackled, should be chosen, preferred to protect these networks, and why? So it's a very long question to answer, but let's see how it goes. Can use this one and yeah.
So yes, I think that the effort that we are doing within Robust 6G, but also in other contexts, is exactly to understand the role of physical layer security in general for 6G networks. First of all, when we talk about physical layer security, we mean several things. There is authentication, but there is also confidentiality, there is privacy, there are many things. And actually, I think that whenever we talk about security in general, in particular about physical layer security, we should clearly understand which specific mechanism we are referring to. Sometimes this term is ambiguous. And what can we do is, and what the effort that we are doing is to integrate physical layer security in a 6G context together with other security mechanisms. In fact, the whole architecture that has been shown before when talking about robust 6G project is about putting everything together, enhancing and highlighting the role of physical layer security because it's new, but all the rest is there. And clearly what is needed is also the exploitation of all the information that is available in the network at different level, at different layers, to increase the security level with attention to the issues about privacy, to the issues about how to handle properly the data, to the issues about complexity. That's why we are also talking about distributed federated learning and this kind of approaches that are kind of getting a whole picture. It's very ambitious. Robust 6G will give some answers there. We'll open also many questions. I don't think we have the ambition to write the standard on our own. So of course, this won't be the ultimate answer to all the questions, but the fact that we are integrating several primitives, several mechanisms is what matters. The alternatives are not alternatives, are things that can be good in different contexts, that can be integrated together. In the alternatives you were mentioning, you were talking about privacy, for example. The privacy principles can find application at the physical layer in similar ways in which, for example, I was discussing the mapping of challenge response authentication from the cryptography domain to the physical layer authentication domain. So you can also push some ideas that were originated in other contexts into the physical layer. But then, for example, you face very specific issues at the physical layer, like the wireless, the propagation of signals. So an issue of privacy there is simply coming by the fact that this signal is going everywhere. And it's very hard to prevent that it's going to an eavesdropper or to someone that is actually willing to get some information about the privacy. And then you have to protect the physical signal itself. So it's a complementary word rather than alternative word in my vision.
Yeah, thanks, Stefano. I think Stefano covered a large part of my answer as well. Just to complement a little bit, we, in the physical layer security community, let's say, at the moment, I think we are focusing to the problems that are not easily solvable with cryptography. Encryption per se is not one of them, because encryption is the most lightweight operation in the whole security protocol. But authentication and key distribution, on the other hand, is, and we have put a lot of effort, and we are putting a lot of effort in these two aspects in the robust 6G project and in other projects as well. And a second point that I wanted to make, because I didn't have the time during my talk, when I was talking about IoT devices being low constrained and in computational power and so on, and latency constraints, we also need to look at the compatibility of the hardware and the software in future generations. This is something we haven't seen before. So, for example, when the communication links, the devices will always be set up to communicate wirelessly. So we can kind of bet that whatever we are proposing with physical layer security, one way or another, if the device is deployed, we should be able to do it even in 10 years from now. But this is not necessarily the case with cryptography, and especially with updating with software patches and so on. This is something that is a new reality that we don't yet have the answer. I think there is a niche there that we can cover. And that's the last point, and I will pass to Tommy. When we look at computational complexity, it is true that a lot of advances have been made in post-quantum cryptography. If you look at what is achievable today, they put a lot of effort, and they can pretty much put very, very complicated algorithms into very, very small devices. But then I will flip the question, and I would say, is it really worth it? Are we going to do this for every simple device that is produced by any random vendor of IoT? Is this the solution? Is this the way forward? So yes, it is possible to put post-quantum crypto on pretty much everything, as they did with before post-quantum crypto, they put AES on RFIDs, and they have showcased actually that it's really not worth the effort. I think we have another niche there when it comes to something that can be around in 10 years from now, and something that can be, let's say, generic. It's not based on the specific characteristic of one device.
Thank you. Well, my take on this, I think, is well, to start with, I wouldn't mind to talk about physical layer trustworthiness in general, because it's security is one part of it, right? But we have dependability on also on accessibility to the infrastructure. Like I showed some that we are doing some more exposure and the network become more vulnerable. So in general, I think physical layer security, or PLT, physical layer trustworthiness, have a role to bridge the digital world and physical world, and anything we can learn from physical world to build a context that helps the digital world to be more trustworthy, but also more efficient. In efficiency, in the sense of, quite often I would say, latency, because there are new applications that are really depending on latency. Many applications depend on cost and ease of deployment and everything. So can we use knowledge in the physical world to implement the context, implement physical world diversity, like spatial diversity in Isaac DMIMO, and redundancy in the hardware and so on? Maybe we can even sometimes relax the physical layer protocols, security protocols in the digital world. If I know that there are, for example, a car, I know that the car is 5 meters long and it's driving a certain speed and it's on a road. And maybe even by sensing information, no, there are no other activity going on. Sure, a very silent, passive eavesdropper on the antenna mountain there in the asphalt 10 years ago, of course. But can we somehow learn the environment, build some kind of initial security trust in the digital world, relax the tracking of the digital paths by knowing what's happening in the physical world? There, I think we have a huge potential. And that way, I think maybe I also can contribute to it, because I'm quite careful in the physical communications world. So that is why I see we might have a role in my team looking forward. And that's what we try to work with Masumo on now, as I highlighted, with this fast slice in the end. Try to learn what are the some offline knowledge and some online tracking knowledge, and what kind of secrets can we generate that are stable for security protocols. So that's roughly my take on this.
Thank you so much. So if I say that basically you all agree, we have opportunities that are at the physical layer. So this randomness that is added by the physical channels should be taken as exploited, as an advantage. And this is coming for free, this randomness, because it's nature that is generating it. Now it's not exploited. And what you're saying is that we should be making good use of that. So first of all, by using this, you can also somehow decrease the level of complexity that we are thinking of or already imposing in the standard crypto algorithms, because we have some underlying schemes that are operating at the physical layer, is what you're saying. And this is basically what your research is about, and is proving what is the level of maturity of this. So you think this is going to be, from what you said also, Elsie, you said that you already had a demo, right, demonstrating some of these capabilities. Is this something that can be is ready for uptake by the industry already right now? Or maybe we have to wait for 5 years to integrate physical layer security, maybe based on angle of arrival or something. We need to start somewhere.
Yeah, actually, the angle of arrival, we were not the first ones to look at it. Okay, we were the first ones to prove that it is a trustworthy feature, if you want. But in the past, there were other groups, for example, Stefan Gilles from Harvard, I think. She was looking at using the angle of arrival for autonomous robots to identify Sybil attacks, which are very hard to identify using traffic analysis and all the standard techniques. And it becomes kind of obvious that when we move towards systems of autonomous agents that take decisions without the human in the loop, take decisions on themselves, their behavior, their physical behavior in the environment and their interaction with the environment should become part of their trustworthiness. So it's not just about the trustworthiness of the AI, is in general the trustworthiness of the device, and the device has a physical presence. And I think this is where we're moving. And at the moment we have, I think, a good bucket of results to move towards pre-standardization of certain aspects. And I think we are, for the first time, getting quite close to the holy grail, let's say, for us that have been working on this since forever, maybe. Yeah.
We are not since ever. Yes, yeah, it's the idea are becoming mature, and definitely we are going towards some, implementation. Of course, there are many steps there. Some possibilities are to go through a standard, which is of course very much welcome. We need involvement of companies because the academia brings things up to the if you want, to the proof of concept in a lab, and then from this to a product or to a standard which is somehow very close to a product, then you need the intervention of companies there because they understand the risk.
On this, you have any idea of whether a standard is being developed and or not?
So it's work in progress. What I would like to say is that, as you have seen, the fact that ITU as a global institution has included physical layer security in this preliminary report is significant in the sense that well, there is an expectation there, and there is a kind of a recommendation. It's also a huge burden, as a huge responsibility for us, I think, because we that are working on this, we have a chance that we have to take, and so we have to be supportive in the process. I would say that there is not only ITU and 3GPP, there are also other standards, if we stay within the standards, that are actually investigating this. For example, standard related to body area networks in IEEE. But also in other contexts, such as Wi-Fi, we expect that there will be some interest. In this sense, for example, I can mention another initiative, which is a cost action within the European Union that is working on physical layer security, which is overlapping in terms of time with the robust 6G. Of course, the nature of this cost action is completely different, but also we are creating a subgroup. I'm also involved in that personally, and we are creating a subgroup that is working on talking with the organization that are doing standards to understand what is missing there, what do they need, and what are how can we help as a research community to actually, investigate and actually at the end push this idea into the standard. So many things are moving. IEEE is also, doing steps in this sense. We are in a maturity of the idea that looks quite very promising to have it implemented in some standard in the near future, with a lot of responsibility on all the actors that are in this arena.
Thank you. I have a feeling that a little bit a little bit different culture in the digital security, computer security world and the physical layer research world. One very important thing is that the physical world is analog. So there are realizations of channels that are continuous, that's a continuous value range. And some, for example, we look into fingerprinting. I mean, what we are interested in is in what kind of channels, what kind of scenarios are there, some kind of way we can generate a fingerprint that is stable for generating common secrets. And that will be a range of parameters. It will work in a certain range, certain deployments, certain situations, and other situations not. So if we do a standard, yes, it means that we support this, but on top of that, we need to co-optimize with the digital security layers, the digital world, the upper layers, security frameworks. When are we, some kind of prediction, some kind of forecasting, understand where are we? Can we trust, is this a scenario where we can trust physical layer mechanism? Or do we need to do it on the upper layers only or jointly optimized? You get we can think about this like a Bayesian way. There's a certain trust. I have the confidence level. Now, my confidence on this physical layer mechanisms are maybe 50%. Okay, that means we can relax some of the upper layer protocols mechanisms, whatever we need it for. If that's a dynamic, yeah, then maybe it is latency and energy. If it is static, yeah, then it's deployment scenario. Is this in an indoor factory scenario? We know the channels very well. We have measured everything. There are just some AGVs moving around, but that's a cruising on the fingerprinting. We can handle it. So here I see, yes, there might be standard hooks. There might be standardization. But how to use it, I think we have a long path to go and to jointly optimize over the layers.
Yeah, what you said now is super important.
Can I also continue on this answer? Because I think you touched a very interesting point. So in classic crypto, the security strength is based on, to put it simply, the length of the key, right? The size of the key. So you have AES 128, AES 256, SHA 512, and so on, okay? These are parameters, and based on these parameters, you can say I have a NIST security level 5 or a NIST security level 1, and I have 100 bits of secrecy, just to give an example. In our case, as Tommy mentioned, the relevant parameters will be, do I have a line of sight? Do I have good SNR? Do I have 100 antennas that I need for this particular technology, and so on? So we can think, and we're actually working on that direction in RobustSecG, for a closed loop automation based on what Pietro was explaining earlier in the morning. We're actually, the closing of the loop for the physical layer security part is playing with those parameters and is actually taking into account, can I increase the power? Do I have enough battery to increase my transmission power if I need to? If I don't, I will switch off this component, this functionality of the physical layer, and I will switch to a different solution if possible. If not possible, then I will give an alert to the orchestrator and we will find an alternative solution. So I think we are far, but not that far. I mean, if I can quote a very old movie, I don't know.
So basically, I like very much your response here, what you said. So it's channel stationarity. So how constant is my channel between Alice and Bob, basically the legitimate users. Then SNR and all these physical things are not stable, 100%, even the fingerprint. So there are ranges. We need to study those ranges. Physical layer security is not like in the algebra, perspective that we are using with Diffie-Hellman right now, that everything works fine every time because this is mathematically, grounded. It's not like that. So maybe there are times where we can generate very secure keys, we can trust. In some other cases, we cannot trust the system because the channel is not permitting us to do so. We need to understand when we can and we cannot, and when we can, definitely this is a resource that we can exploit to make the system more secure. So am I correct in this, what I'm saying? Yeah.
Yeah.
Yeah, but even in a cryptographic switch, I mean, there is a negotiation of those parameters. So if you run TLS, it's not like you're going to use 100% this type of encryption. There's a negotiation. So I think we can envision moving towards that direction in physical layer security, where some of the parameters are negotiated during, I don't know, a setup stage.
It's also a matter of how important it is to try. How much do we benefit and give situation from the physical layer security help on higher layers, so you can relax the upper layers? What's the benefit on doing that? That depends also on the application, the scenario, and so on. And what I want to highlight is with some of those technologies I touched upon, and Stefano also, on where we spatial distribute the antennas for RIS and DMIMO. We are also, compared to a single base station where we have one channel, a static environment, the fingerprint will be somewhat static. With RES, we can reprogram the channel. We can adjust the properties of the fingerprint and control some of the uncertainties. When in general, when it comes to MIMO technologies, that's what we try to do all the time. We try to measure and track the channels, because channel state information at the transmitter side, CSIT, that's the holy grail. And in my last rushed slides here, I try to highlight that we are going towards deterministic communications. More and more line of sight, more and more learning the propagation environment, but on top of that, also try to control it towards deterministic cables, as we have been used to in cable-based communications. So RIS is one way. We are changing the phases, the delays, and so on, and even absorbing some energy. In DMIMO, you can view that as a further generalization on our RES, because with DMIMO, we can inject new power. And we have many antenna elements. We can do it independently per antenna element, and still we can freely control the phase. Not only the relative phase, because on RES you get in the signal from certain direction with a certain phases, you are doing a relative beamforming according to the incoming wave direction. With DMIMO, you are decoding forward. You take in the signal, you regenerate in a certain direction. So with DMIMO and combining with ISAC, you can fully control, in theory, the channel knowledge. So the question is it worth it? Depend on the situation.
To complement, there are new parameters. We can use these parameters to decide what to do. There are also a possibility to control the channels, or to control this analog world, but I think there is also the need to better understand, or to complete the understanding of which are the security fundamentals that are behind physical layer security, in the sense that as you change the paradigm, as you move from encryption and that kind of security, computer science security, and you go to a physical layer security, new areas, new threat surfaces appear, and then you have to understand how to withstand these problems. So, for example, in cryptography, you are interested in a number of secret keys secret bits that you can exploit, which is still relevant also in a physical security context, where you can have the equivalent of bits in terms of number of attacks that makes the attacks successful. But you also have other surfaces. So, how many antennas do the attacker need? Which is the knowledge that the attacker needs or can get to actually break the system. So these other scaling laws, these other information are also to be explored.
Yeah, one more. Yeah.
One last question.
Yeah, okay. Sorry, just one point, because I think we kind of all took it for granted here, because this is what we are working on. The threat model changes in the sense that in physical air security, there needs to be physical presence of the attacker, as opposed to I can hack a system and from, I don't know, Arizona, whatever, Utah, attack Dublin. I cannot do that. I need to either have penetrated the premises and installed devices, or have legitimate access to that venue, let's say. This is different.
This is an advantage, an additional advantage, because if you don't have access to the premises, you cannot implement a physical layer attack. This is what you're saying, right? Yeah. So it is a completely new dimension that we can take advantage of. Now, my questions are, we are towards the end, and they asked me to close it, because now we need a break and we need to close the day. It was super interesting. Probably we could go until tomorrow. But last question that I have in my mind is complexity related. So all that is very nice, but how is this complexity of the whole system? You mentioned that in your presentation. Is it going to explode, too big to be managed? Or maybe we can make it work even in a low complexity system? And also, when you answer, try to also analyze the role of artificial intelligence, if any at all. Do we want AI? We don't want it? Yeah.
Short question, short answer. Generally speaking, the physical air security has a low complexity because it operates on signals, and it has a lightweight approach there. We have to see which is the complexity in terms of hardware, so number of antennas, the kind of things, and that is related to what I mentioned before. For artificial intelligence, it can play a very important role, because there are many phenomena that are complex and are basically dominated better by using artificial intelligence. There is a huge problem of prediction, for example, for the channel state information, and their prediction using artificial intelligence can be very nice, but also, many other things that are related to authentication, for example, or to privacy, that can be easily tackled with artificial intelligence.
Yeah, to answer quickly to your question, with the help of machine learning, we intend to do an authentication and key agreement protocol that achieves a less than 5 millisecond time. I think this beats everything that is around today. And well, the more we will have demonstrators and test beds, and then we can even start measuring number of gates and stuff like that, as they do in cryptography. We don't have that yet available. So based on the early comparisons, it is clear that we can fuse parts of the communication with the security. And I think this is a win-win, because the total delay for both phases can be synergetically reduced.
So in general, in my field, my experience is that there are often diminishing return in complexity. For example, macrodiversity, two antennas instead of one helps a lot. 4 antennas instead of one helps a lot. 8 still worthwhile. 16, it's not really worth it. 22, no, it starts to diminishing. There are quite often logarithmic effects here. So with complexity, I think yeah, it depends once again on the data question, what is worth to do complexity. When it comes to AI, I think at least there should be a lot of potential to use ML AI to learn how to design or how to find the common secrets from the physical properties. Because it might not be that channel state information or hands-on as a fingerprint is the best. There might be other monolithic properties that are more invariant, they're more stable, but we don't know them. So by working a lot offline on exploring that in a free running way with maybe deep learning. I think that there should be some potential there. We might find another way of thinking. Ideally, if we try to understand what comes out and go back to some theory understanding. And that I think is worth a lot complexity to do. Then how much we should do online, that we need to do the math on in the end and see if it's worth it or not. On the other hand, it's not for free to do it on the upper layers too. I still remember from 4G times, we looked into should we do adaptive transmission and different residual bit rates because we had different service classes on still voice thinking and so on. And then turn out with LPC code or turbo codes that they are so steep in the SNR curves. So with if we need to have a reliability of 10 to minus 6 for the decryption algorithms, we need to have 10 to minus 9 in the bit rate on the raw bits. So it was not worth it. There was 0.2 dB gain roughly to implement the adaptive residual bit rate adaptive transmission schemes. So we skipped it. We went for the same target bit rate for all the services, and because we want everything to be encrypted. So I think this kind of detailed interplay and common analysis are quite important too when it comes to the end performance metrics here.
Now time is running out, so I thought about many more questions, but many of them were covered. I have one last question for you guys, and then we ask the audience if they also have a question. So I summarize it in this. What are the key, maybe 2 key new features, security features that will be needed by 6G and beyond? And how is this physical layer security capable of supporting in this direction? It's tough. Huh?
Yeah, I mean, I think I will repeat myself here. So we're looking at systems of autonomous agents. This is the most, I think, demanding use case scenario for what is coming. And I believe that in that scenario, physical awareness and building on the physical awareness, physical layer security can actually bring solutions. Because as I tried to say before, the physical behavior of a device can actually circumvent the need to run very, very elaborate upper layer tests in many cases, not in all cases.
Well, I would say authentication and privacy. These are the 2 probably most important things. Authentication because it's quite, I think, mature. Privacy because it's mature, but also because it's quite relevant and, I mean, must be addressed at the physical layer.
Was the question related only to physical layer or in general for 6G?
Needed features that will
Yeah.
for future networks, and then how physical layer security is out.
Yeah. I think we haven't touched so much about sensing, integrated sensing in 6G. We haven't talked so much about it in this panel. But that is quite disruptive for a mobile network to be able to do radar sensing by the access points, maybe even by the mobile phones in a very integrated way. There, I think we really have a trust issue to the communities we are approaching, and that will be everyone in the society, that we can trust this network. Is it sniffing on you or now or not? And what information is it collecting, and where it's staying, where it's going? Have I control? Can I impact that or not? This is one of the key values I think we need to be able to address as a community to convince everyone that this is a good system to use. So I'm going a little bit out of the general, what we talked about before. The other for me is that are very disruptive is, of course, the AI-driven networking. And we need that for efficiency of the automation of we cannot do manual configuration and tracking and everything. It doesn't scale. It should be cheaper, still more complex. So there we have a huge challenge, I think, when it comes to secure the data, the training data, the offline. On the other hand, if that ends up as an algorithm, we can still test it as usual. But if this is our online data, we are learning and using in the network as part of the privacy and the trustworthiness mechanism, then I think, how do we quality control that? One rotten egg leaking in might destroy the whole cake. So I think Robot 6G is at the heart of this, and that is our challenge. The online use of data, learning data.
Excellent. We conclude with one question from the audience, if you guys have some curiosity.
Context information created by the help of layers. So I see that the context or the environment could be very diverse, and I just wonder how or is there any studies trying to address these challenges? Maybe generating models which could be implemented everywhere will not be that easy because there will be very diverse environments and it will be quite challenging to use generalizable models everywhere.
Yeah, I didn't have the time to talk about this ladder in my trustworthiness slide during my talk, based on what Tommy also mentioned. So in the near future, we will have a lot of sensing data, and we will need some, let's say, semantic analysis to find out which part of that data, because we cannot deal with the full data set. I mean, it's impossible. We cannot imagine that every single agent will non-stop run an analysis of the whole network. It's impossible. So we need to boil down with what we call semantic compression in our community. What is the relevant part? And this is not just merely a feature selection. It goes far and beyond, and it reaches what we call goal-oriented communication. So based on the final goal, based on what the system tries to achieve, there is a kind of feedback loop that lets you decide what part of this whole information should be kept and is relevant, how this combines with information from other agents in other parts of the network, root cause analysis and so on, and then fusing everything together at upper layers in order to make the final decisions to drive the whole thing. So this is how, that's my take on it. But this is still on paper. I don't think this has been done yet. This is, I don't think it's for the first phase of standardization. We're looking towards the end of the standardization procedure for this type of techniques.
Okay. Let's see if my answer addresses your question correctly. What that triggered on was I see a little bit on opportunity to start to have some adaptive trust level in the system, not aiming for perfect security all the time, because that maybe costs too much in time, in energy, in complexity, and it doesn't scale. So can we somehow have adaptive trust here where we in some tracking situations are highlighted, we relax the trust because we have some context, we believe it. What's the consequence of a failure when we talk about goal-oriented? Because there you have, typically some asymmetry, right? Succeed and failure are not always symmetric. So can we configure the security system based on this? And then lower the ambition on the higher layers when we can live with the consequence of a failure, because we gain on other metrics like inefficiency, on complexity and so on.
If I see it correctly, I understand what you said is perfect, but maybe the problem is to have like a model of the system that is covering all the possible scenarios so that you don't need to adapt the model according to the problem or the type of channel, or so the model should be somehow covering all the possible channels and scenarios of physical air environment that you may encounter. And then on top of that, you may have some features that are created by the model that may be like trustworthiness, or that can be like a soft value going from 0 to 1, and then you can adapt. But are we nowadays in the case where we can? I'm telling you now, I need authentication. I need to implement it, and you don't need to come up with 10 different models. And you say, okay, if you are in a school, you're using this one. If you are in the bus, you're using this other model. If you have like a universal, like sort of way of covering all this stuff, and then out of it, we can get the soft values that you were mentioning to adapt the security.
I mean, we need to find the solution for the most difficult case. But if we then can have some kind of gears here, we have different levels. And then we can switch to the relaxed when we see that is a possibility. Because also an application, say that this security layer now or mechanism are, for example, to an autonomous vehicle. But then we also had opportunity in the control algorithm of the vehicle to lower the speed. If I don't have enough information here, I don't trust the external sensor information I got because the channel is not secure, the source is not fully secured. I have my on board, but my trust level a little bit weaker now, so I better go down in the speed. That's what we do when doing manual driving as a human too. Say, okay, seems to be slippery. I'm from Sweden. There are some icy roads sometimes. We lower the speed if I don't trust that they have grip enough. Even though normally I'm capable to go on max speed according to what's allowed. But if we have the mechanism we have proven under good conditions, we cannot have close to 100% trust. And when that's needed, we do what it takes in these solutions, jointly optimized over the higher layers and the physical layer security. When we can relax it, we relax it. When it's too costly or we don't even know we can get information fully, we tell that to the application, okay, the application can go down on the aggressiveness, on the how to use this information that's not fully trustworthy.
Thank you so much. So we need to close it. You want to say last word, but otherwise we close.
Yeah, a few years back, I think it was a colleague from Dula, someone from Thales has coined the term quality of security. And in that aspect, and basically continuing what Tommy mentioned, we could think of best effort security as we do best effort links when necessary. For example, in a non-critical application, instead of having nothing, because at the moment there is a lot of IoT networks where we have nothing, we can actually think of best effort security or update the trust and reputation management of the upper layers to incorporate physical layer aspects that can actually make us listen, but not 100% fully trust some untrusted or not so trustworthy information that comes from the outside.
Okay, so with that, we are out of time. So we're going to close the panel. I'd like to thank the panelists. It was an amazing session. So thank you and well done. Thank you, Mikael, for leading the panel and asking very important, difficult questions that made us all think. At the same time, we are concluding with SecureNet 2025. We'd like to, I guess, invite you to SecureNet 2026, which is likely to be also in Dublin, unless the school approves to make it happen in Vegas. But it's as likely as deploying 6G this year. So it's going to be Dublin. You're all invited. The YouTube recording from this session is going to be available right after this session closes. So if you want to share it with your colleagues, we are also going to be making smaller videos in chunks so that you don't have to watch the whole 8 hours. And once more, I'd like to thank all the presenters. And for those that stay for Robust 6G meeting. I'll see you tomorrow. But we do still have coffee today and perhaps some snacks. Are there snacks there? Okay, so snacks and coffee, you can grab that on the way out. Perhaps it's the last chance to catch up with the presenters, exchange your LinkedIn profiles or your mobile numbers. So once more, thank you, Sam. Gunesh, some last.
Maybe share that generate challenges related to physical data security out of the non-technology project. There may be some people like them from the audience who would like to address issues, follow our presentation.
Yeah, definitely. So I do recommend visiting robust6g.eu with yeah, subscribe. But no, seriously, with all the seriousness, we do have a lot of demo videos where you can see the project in action, not just in form of a publications, but also in form of a hands-on experiments. Thank you so much for to everyone presenting and attending, and I'll see you next year.
And a round of applause for Bart here who organized this wonderful event. Yes.
Yeah, I'll just put it here. Thank you so much.